Hi everyone, good morning.
Very good morning, sir. We'll be starting just soon. We'll just be waiting for a minute more for other participants to join, and then we'll be starting our session.
I just wish to inform that I'll have hard stop at 12.
Pardon me, sir. My microphone was disconnected. Can you please repeat?
I was just telling that I'll have hard stop at 12.
Okay, sure, sir. We'll take care of that.
Okay.
So I think it's about time that we start our session for today. To start with, first of all, I'd like to greet everybody. So good morning, everyone. A warm welcome to today's Capstone Student Presentation session. That is a key part for the first summer school on deep learning, shaping the future of AI, organized by IIITDM Jabalpur. After 4 rigorous weeks of immersive learning, hands-on assignments, and expert lectures, it's now time to witness the culmination of our participants' efforts through their capstone project presentations. This session features top performing students who have demonstrated outstanding engagement, curiosity, and creative throughout the program. Today, we will present innovative projects that apply the deep learning concepts they have learned to solve the real-world problems. Moving on, we are deeply honored to have an eminent evaluation panel with us today for this amazing session. To start with, we have Professor Jimson Mathew from IIT Patna, a leading researcher in deep learning and hardware security with international academic experience. Then we have with us Dr. Ranjeet Kumar Ranjan from IIITDM Jabalpur, an expert academician in machine learning, soft computing, and cybersecurity. And not least but last, Dr. Ravi Ranjan Karn Associate Director of Accenture, and industry veteran in GenAI and data-driven AI/ML solutions. We are delighted to have all these amazing panelists with us today. These respected panelists bring with them a wealth of academic and industry experience. We are grateful for their time and insights. So today we will be having different sessions of the top performing students. And I'd like to start the session with introducing, and then each student or team will have, I'd like to put down some ground rules first. Each student or team will have approximately 8 to 10 minutes to present their project, and then it will be followed by a brief Q&A and the feedback from the panel. So just give me a second and I'll be calling the first team to present us with their presentations. Thank you. To start with, the first panel or the first student that we will address today is Swarnajit Mandal. Are you present? Just give me a second. I will enable the microphone access. Okay, now all the participants can unmute themselves. Can I please have Swarnajit Mandal with us? Okay.
Yes, hello.
Yes, Shubham Kumar. Swarnajit Mondal. If the participant is not present in the meeting, we will be moving.
I am present.
Okay, okay. Okay, so this is Swarnajit Mondal.
Yes.
Okay, sure. So please, can you share your screen and start with the presentation?
Just once confirm me if it's I could see my screen.
Sure.
I guess it's good enough.
It is, it is. We are able to see your presentation.
St. Elisha deemed to be university is dead.
Shall I start now?
Sure, you can start.
So hello everyone, I am Swarnajit Mondol and my project is facial emotion recognition using deep learning. It was developed using the FIR 2013 dataset with a CNN-based architecture implemented in PyTorch. The goal was to solve a real-world computer vision task using the deep learning concept covered in this summer school. Let me introduce myself a little more. I am a student from Kalinga Institute of Technology, and I am learning the topics on CNN and the transformer from the summer school. Okay, let's continue on this project. Let's now talk about the problem statement. Emotion recognition for facial image is a well-known challenge in computer vision. The problem is to classify a face image into one of 7 emotions. The model must be robust to various like lightning, angle, and facial shapes. The emotions it detects are happy, sadness, neutral, disgust, fear, anger, etc. I will come to that later. Okay, so the next slide is our problem statement, problems and motivation. So the facial expression analysis has application in mental health monitoring, online education, driver fatigue detection, and effective computing. With the rise of AI in assistive technologies, automating these tasks can enhance responsiveness and empathy in machines. Okay, so let's just talk about my data set. What is the data set? I use the FER 2013 data set. It is 48 into 48 pixel grayscale face image labeled with 7 emotions, as I said before. It contains like 35,000 samples split into train and test set. One issue with the dataset is its class imbalance. especially under representation of the disgust class. Like it has numerous images of happy, neutral, sad, but it has like very few images on disgust. So it made my accuracy very low and it was hard to make my model learn the disgust. It was quite hard. So next, let's go towards its application. Okay, let's discuss about the model architecture. At first, I made my own model. It had like few convolutional layer, ReLU layer, max pooling, and dropout, and a fully connected layer. And after that, a flattening layer to just classify it into classes. But it gave like 60% something accuracy. Later, I then moved towards pre-trained model. It was a ResNet 18. Yeah, now let's talk about the training strategy and loss handling. I trained the model for 50 epochs using Adam optimizer, and loss entropy was cross entropy loss with a class weight of. I use a scalar function to just address the imbalance so that every class get the same opportunity to learn by the model. Then I use data argumentation like horizontal flip normalization to improve the generalization. The learning rate was pretty low. It was like 0.001, and then I also use scheduler to, if my model just that overfit, we can just slow down the learning rate. Then let's talk about the metric evolution metrics. Okay, let me show you something. The output. Let me show you. Okay, as you can see, the confusion matrix. It pretty well detected the angry, then the fear, then the happy, then sad, surprise, and neutral. And the disgust one is very less because it had, as I said, it had very few images. But then I fine tuned it, and then like as I said, data argumentation and increase the disgust value through flip, horizontal, and those argumentation. Okay, now. Okay, so let's talk about some. Let's talk about the challenges I faced. So the main challenge I faced was class imbalance, resolved partly with weight loss and data argumentation. And I also tried to integrate my webcam with it, but Google Colab didn't help much with that, so I need to postpone that. And then also I tried to use the Daisy data set to make my model learn, but as it was so big in size, I couldn't like handle it properly, and within the time frame I couldn't complete the task. And also real world deployment required a lightning operational and cultural variance, so I will work it later on it. Okay, so what are the future works I can do? So as I talked about the challenges and the future challenges, so I can probably work on the challenges I face and overcome it, and add more emotions like anxiety, confusions, depression, drowsiness. Adding this will also help in uh, recognizing the emotions of student. As we know, India has a pretty high suicide rates in India of student. So these things may help if my model gets successful. Yeah, this was the conclusion part and all. And thank you. You can ask any question if you have. I guess the presentation was well.
Well, if any of the panelists have any query or any question for the participant, so we can move with that.
Yeah, just wanted to know how many days you took to do this project.
I take 2 days.
To come again, please.
Hello? Sorry?
Yeah. So how
Uh,
many
I
days?
took
Uh-huh.
I took 2 days.
Okay, so you were able to do in 2 days. Okay. And what,
और
uh,
बोले मीटिंग चल शो चार
okay. And what did you do for, working on class imbalance that you discussed about?
For class imbalance, I separately use transform to the discuss data set so that it gets few new angles so that the model can learn.
Okay.
Like I not like just transform all the data. Like it would be same in that case. So I just applied the transform on the discuss data set. And I put on weight separately through the optimizer so that it understands the if it is discussed, then it can learn more properly.
Okay. And which data set did you use?
It's FER 2013. I also tried the Daisy one, which I downloaded from IIT Hyderabad, I guess. But as it was very large, it was 15 GB, so my Google Colab can't upload it, so I couldn't do it in the time frame of 2 days.
Okay.
I
Okay.
will do it later.
Okay.
Any more questions? Okay, so I think we can move forward with our next participant now. Before that, thank you, Sir Najit. I think your project reflects how much effort you have put in understanding the problem statement. Thank you. So next we have with
Thank
us,
you.
thank you, Hari Krishna. If you're present in the meeting, please can you share your screen?
Hello,
Hello.
hello. Hello.
Hello. Yes, Hari Krishna, you're audible. Please continue.
Just a minute, I'll share my screen.
Sure.
Is my screen visible?
Yes, it is.
Okay, then I'll then start with my presentation. Is it okay now?
Yes, we can clearly see it.
Yeah, okay. A very good morning to all the respected panel members and professors, working professionals, and my dear colleague, Deep Learning Summer School mates. So let's start with the presentation here. So my topic was like creating a unique model which segments the liver and liver tumor. So okay, let me introduce myself. I'm Ari Krishna. I'm an MTech student here at IIITDM Jabalpur. So without any lag, we'll proceed. Okay, coming to the problem statement, as we already know, in recent years, in 2022, the cancer cases are like very huge, like around 8 lakh cases are there. So it's very, and from CT scans, like which represent the liver and liver tumor. So manual identification is a bit a challenging task, right? So as we know, like, and deep learning is in every domain. So obviously we will build some deep learning model which will segment the liver and liver tumor part from the images. Okay, and yeah, this is a basic problem statement now. And obviously, yeah, cancer is like liver cancer is one of the leading causes of deaths and all. And obviously, it is like fifth or sixth most cancers among men, and eighth most leading cancer among women also. So it is like we should pay very high attention to this. And yeah, now let's these are some of the state of art models which worked on these data set. Um, which worked on the liver, especially liver and liver tumor segmentation. And these are some, like, they have achieved some 95.7% dissimilarity score for, for liver, and 75.6% tumor segmentation, like DSC score. So okay, don't worry about this. Like we'll go through the final results as well. So yeah, coming to the data set, this is very popular data set and publicly available data set, which is 2017 MICCI challenge data set. Uh, Basically, this data set contains like 131 scans. Like these are like 3D scans, like 3D scans in the sense like if we take a slice from one like these scans, it will be like a 2D image. So these will be like so yeah for pre-processing, like we need to convert these 3D volumetric scans into 2D slices so that we can obtain the image part. So these image actually contain obviously two primary classes, which are liver and tumor, and another one is obviously background. So images and mask will be present. So like yeah, these are like around, actually there are more images like 30,000, 40,000 images, but I'm concentrating on mostly the images which contain primarily the liver and tumor part as well, like which have the mask of liver and liver tumor as well. So yeah, the images which has the both classes, those particular images I'm concentrating on. And actually there are around 8,000 images which actually contain that particular mask contain liver and tumor as well. So out of those, due to my resources constraint, I'm just considering only 2,000 images. Okay, yeah, these are some of the sample images from the dataset. As you can see, yeah, this is a one image slice from the scan from 130, scan number 130. Yeah, this is actually the abdominal scan. Okay, from this we need to segment the liver part and the tumor part as well. If you see the green color portion, this is a green color portion, like this is a part which has the liver, and in that liver, this is a red color. As you see, the red color portion, the small, this is the tumor part. If you can observe here, this is the liver part, and this small variation, like a light black color, like light gray color. This is the portion which has tumor. So if that tumor is not present, it will be all green, and there will be no tumor present. Okay, the red color indicates that there is tumor in that. So these are some of the sample images from the dataset. And now, yeah, coming to the pre-processing part, as you can see from the previous images, if we, here we can't able to identify that much difference between the liver and tumor, right? Because obviously these pixels between the liver region and tumor regions are almost identical. Like we need to, the model should differentiate, right? The intensity variation should be like very, differentiable. That's the main task. So what I did was I have applied, yeah, sorry. Yeah, I have applied histogram equalization technique, which actually, redistribute the pixel intensity throughout the image so that we can clearly observe the differences between the tumor region and pixel region. So I am resizing all images to 56 cross 56 for my model, and I have did some data augmentation parts like brightness, adjustment, rotations, flips, and all those things. And obviously, I need to scale my pixel values to 0 to 1, for stable training. So yeah, as you can see, this is my pre-processed images. Like this is the original one, and this is my histogram equalization. If you see my histogram equalization, like the pre-processed image, the intensity variance are like very visible. The contrast is very good, and if you see the entropy is almost same, but the sharpness also got increased and the contrast is also increased, right? So if you see here, the tumor part is clearly visible, and yeah, and the tumor part is clearly visible from the liver part, right? So this is the advantage of this pre-processed technique. So uh, just yeah, coming to the model architecture now, the pre-processing part is done, and coming to the model architecture, here I have used a hybrid model. In general, segmentation models are like traditional models, right? As we know, UNet part, which consists of the encoder part and the decoder part. But like, what's the problem of, as you know, the encoder part of UNet consists of like multiple convolution layers, And we already know that convolution layers are very good in extracting the local features, right? So we obviously know which has like evolved like very greatly, which captures the long-term, the long-term dependencies as well in throughout the image, which captures the global content. So I thought of like using vision transformer, right? So what I did was in the traditional unit model, we consider that it consists of like a unit part and like encoder part and decoder part, right? So the encoder part, which in traditional unit, take the applies the convolution layer and downsample again, extract some features again, downsample, and that's what it is, right? From the decoder part, actually like apply convolution transpose convolution and quietly upsample that. So what I did was like encoder part, which is the main extraction part. What I did was I replaced it with the vision transformer because obviously my unit, encoder part will capture local features very nicely. That's okay. But here I'm using vision transformer as my encoder part so that it also captures the global, global things, right? Global features. So and as majorly like wit was used for classification, but now I'm using wit as a encoder part so that I can extract the global feature, and I'm using that features as an input to my decoder, as our problem statement is segmentation. Okay, and now as you can see that my encoder is with a vision transformer, and I'm splitting into the 1616 patches, and I'll explain these things. Just a minute, yeah. If you see the, obviously know, all of you know that this is our vision transformer. As you can see, our image is getting divided into several patches, and each patch has a position embedding, so that because when we divide the image, we should know like which part is from like which part of the image, which patch is from which part of the image, right? So that's why we are obviously encoding the position embedding. So these position embedding will passes to the transformer encoder. And what is this transformer encoder? As we already know, this is the transformer encoder block. These embedded patches are passed to the layer normalization layer, and these LN and MLP layers are like used for stable training, and this is a multi-scale head attention, right? So these multi-scale head attention, like I have used 4 heads in which each head captures different types of features, and yeah, that's it. So these MS is very crucial, right? Here the attention or oral attention takes place, and this is very crucial for our information extraction. So yeah, now coming to this is the encoder part. Now I have passed it through like I have used 4 transformer blocks, which extracts like multiple features, and the finalizes features I am passing through to my decoder. And here the decoder part is similar to our traditional unit, okay? And which contains of, obviously I already told you, transpose convolution and upsampling layers. Okay, just a minute. Yeah. Yeah, as I already told you that decoder is similar to unit decoder. Now I already told you I have resized the images to 56 cross 56. That will be our input, which passes through several transformer blocks, and then again the decoder followed by the decoder. So the output will be again a 256 cross 256 segmentation mark, which we want to get with obviously 2 channels. Here I'm ignoring the background class because obviously we don't need it. We will be concentrating on the liver and liver tumor class. Okay. And yeah, coming to the training setup and strategy, obviously our main task is to extract the 2 class segmentation. I'm ignoring the background, and obviously my device, like whatever GPU I'm using, like very less RAM. So obviously resource constraint will be there. And these are the hyperparameters which I'm using: batch size of 2, and optimizer RM, and this is the landing rate, and loss function binary cross entropy, which does which will be calculating pixel and pixel wise, right? My ground truth mask will be there, and my predicted mask will be there, and it will calculate the loss function. And number of epochs are 15, and these are the metrics. See here, metrics IOU and dissimilarity score, like both of them are almost similar, because they almost like IOU dissimilarity score gives more priority to the intersection part. Like this is a ground truth mask will be there, and a predicted mask will be there, and it tries to calculate the intersection between the regions, so that if it is high, we can say that our model is exactly predicting the tumor regions and liver part as well. So yeah, and coming to the results and evaluation, yeah, the liver was the model was performed absolutely very well for liver. As you see, the dice coefficient is like 0.96%, which is very good. And coming to the tumor part, it is not that good. Actually, not only my model, like in general, I have studied so far, like in general, the state of models are not performing very well on tumor. Why? The reason is, as you can see from the images, the tumor part is very minute compared to the liver part, right? So obviously, concentrating on that smaller regions is very crucial. So that's why, like, obviously, my model also failed for that, like not failed, but reasonable value. I achieved at 0.78%, but for liver, it's absolutely very good. So yeah, these are my predicted topics. You can see this is my histogram equalized image which I am giving, and this is the ground truth liver, which this is the liver part actually. And if you see my model is predicting the liver, very almost very good. But predicting the tumor part, like these black regions are there. These are the tumor parts, and for some images it is predicting very good. For example, here it is not that much accurate, right? And for here also, like it excluded, I think here some of the regions. So if it is very crucial, identification of tumor is very crucial, because if the patient is already having the tumor and our model is not able to predict the tumor, like it will be very, it will be a very high penalties, right? So yeah, my model is doing very good for liver portion compared to the state of art models, but for predicting tumor, like I need to, develop this is also one of the concerns which I'm having very limited resources. So I was not able to experiment many models. So yeah, that's the thing. If you see training is also very stable, the loss is gradually decreasing. And here also, if you see the liver, IOU and ICE are like gradually increasing. Um, yeah, and for tumor also, like it is very gradually increasing. So, and yeah, obviously the challenge phase it was like, obviously tumors are like very small, irregular, and obviously low constant, and also class imbalance is present. Class imbalance in the sense, like the tumor part, like you have already seen, right? The tumor part is very less compared to the overall liver part, right? So that's why, and in total image also, if you compare the total image also, like the tumor part is very less compared to the total image. So when we applying a vision transformer like on overall image, like it is obviously like at some 2% to 3%. So that is a challenging part. And yeah, and I need to overcome these challenges by using, by experimenting different models. And yeah, that's the conclusion part. And yeah, future work, what I wanted to do is like I want to try like more deeper models. Like as of now, I am having very limited resources. I was able to perform like this much only. So if I have like if we have a good resources, we can experiment some different models or some deep layers. And also another thing is that if you see convolution visual transformer, so far whatever models, these models are performing vision transformer on total image, right? So see, we already know that tumor is present inside the liver part only. So why to attend all these things if we know that our tumor is present in the liver portion only? So this is the idea I got, which I wanted to implement in future. So if you see, first I will take the liver, okay? What I will do is I will multiply this mask with the input image so that I can get the liver region. Right. So when I get the liver region, I will apply the vision transformer on that liver region only, so that my attention for tumor will be more, right? So that is one of the tasks which I wanted to do. And yeah, that's it. These are some references, and thank you. If you have any doubts, you're welcome. Hello.
Yes, Hare Krishna. Any questions from the panel?
Yeah, it was a nice presentation, Hare Krishna. Myself, Mr. M. Rajesh Kumar.
Yes, sir, yeah.
Yeah, actually, you mentioned about the segmentation part. Is there any particular tool you have used for segmenting that masking the regions, or it
Uh,
typically done by unit?
so like I just no, I have done through the custom PyTorch model. Like whatever training I have done, that's I have used I have developed my own custom PyTorch model, and I have trained. That's it.
Okay. Then how can we separate? You have talked about the future region you are going to work on separatable tumor and liver region.
Yeah. As I
Tumor.
already told you, sir, like first first task is to predict the liver area, right? So after we get the liver mass, what we'll do is we'll multiply, so we can get the exact like whatever predicted liver region from the input image. As we already know, the tumor is present in the so. For extracting, like there are, I need to, see some ROI, right, region oriented, like extracting, models or something like that, so that I can extract the exact boundary or, bounding box kind of thing, so that, I can extract the exact liver area from the image.
Okay.
Yeah,
So
I need to.
we talked about data augmentation.
Yeah,
You use some three techniques, right?
yeah.
So why can't we go for medical images, some more new techniques? Is it possible to take?
Uh, like new techniques in the sense like for a data augmentation.
Yeah. Because
Uh,
the general thing everyone is doing, like, so you can, if we follow some other techniques, there will be some increasing percentage of finding tumor maybe.
yeah, yes, sir, definitely. I will go through it in the future. Like for now, like I use just the traditional augmentation methods,
So we
like
can add
like
some noisy techniques maybe possible.
yeah, definitely, sir, definitely.
Okay.
Thank you, sir. Thank you.
Okay, so I think we do not have questions for. So thank you, Hari Krishna. I believe, this was an amazing explanation, and I hope that you move forward with this particular model so that it could be used in some real world applications. Thank you.
Yeah, thank you for giving this opportunity.
So moving on to our next participant, we have with us Abbas Hakimi.
Yes, can you hear me?
Yes, we can. Can you please share your screen and start with the presentation?
Okay. 2 minutes. Yes. So, yeah, good morning, everyone. This is myself, Abbas Hakimi. I am a student of BTech from IIIT Vadodara. And my topic for the Capstone project is Parkinson's disease detection by using time series analysis. So, let's quickly start. Uh, so, basically Parkinson's disease is a progressive neurological order, and its symptoms mainly include like slow movements, tremors, and muscle stiffness. So there are various different solutions for detecting its symptoms, which include image classification of basically drawings of the patients. But the solution I have implemented is by studying the handwriting dynamics over time. So which can be a low cost and feasible solution. And basically it studies the distortion in the handwriting, like shakiness, hesitation, and irregular pressure. So basically it is a basically binary classification kind of problem, which will check whether the person has the symptom of Parkinson's or not. So basically my data set includes the UCI's Parkinson's handwriting data set. It basically into two classes, Parkinson and healthy control patients. And during the collection of the data set, there are mainly three tests done on the patients, which is the like static spiral, dynamic spiral, and circular motion. In circular motion, basically the patient have to draw like circular patterns along a point, and static and dynamic are patient have to draw spirals based on blinking and static patterns. Like basically they have to trace the patterns to detect their data, and it is basically contains CSV values of x y coordinates over time, and z is basically the pen is on the paper or not. Includes pressure, grip angle, timestamp, and the test ID of the test. Basically, yes, this is I have Parkinson's 62 subjects, and control 15 subjects. So basically, this is there is a class imbalance in the data, which we'll address later with weight loss and data augmentation. So I have pre-processed the data by basically normalizing the XY values over time, and I have taken a fixed length of 200 steps, and during splitting of the data, I have done the stratified splitting to preserve the class ratio in all the training, testing, and validation data. So we have like 60% training, 20% validation, and 20% test data in the whole data set. And to like control the class imbalance, I have I have done data augmentation, like adding Gaussian noise by jittering and resize and scaling the data and randomly resizing it by scale factor, and shifting also shifting them XY coordinates to increase the variability. And I have used min max scaler for the normalization here. So basically, this is the main model architecture I've used. I like tried 2-3 models. First, I tried LSTM, but the accuracy was very low, but because we have to like extract the spatial features also. So then I tried CNN, but then instead of LSTM, I tried this bidirectional GRU. And to increase the learning, I also tried an attention mechanism with it. So basically, we have initially we are taking input 6 channels, and we are passing through 1D convolutional layers because it is 1D time series data. So we are extracting some local spatial patterns in it, and then we are simply passing it to the bidirectional GRU. In the basically we are using ReLU plus standard ReLU and max pooling, and then we are passing it to the GRU bidirectional. So the hidden states are basically 128 in it, and we are performing layer normalization. Of the two output, we will get 256 because it is the double, because it is bidirectional, and then we are calculating the attention weights via the default attention layer of PyTorch. And by those attention weights, basically we'll focus on the key parts of the sequence that in wherever the sequence that is more required to focus. For example, in such a sequence, where are the most shaky and hesitable parts in the handwriting? And because and by using those weights, we are basically calculating our context vector and passing it to the final fully connected dense layer to classify both the classes control and prediction Parkinson. And during training, I took over 25 epochs with a learning rate of 0.001. And the main is that I used the loss function of, I did not use the standard binary cross entropy for this classification. Instead, I used the weighted cross entropy to handle the class imbalance. Because as I told you, we have control is the minority class. So we assign the weights, higher weights to the minority class uh, so that the misclassification will be punished differently for both the classes. And we take the batch size of 32. And these are the evaluation metrics. As you can see, uh, for the Parkinson, the F1 score and recall are very good, but for the control, it is doing slightly poor. And in the confusion metrics also, you can see the two positives for the Parkinson are very high, and in control it is doing slightly average. So this is our training accuracy is basically 95%, and because of the class imbalance, it is slightly overfitting, and the validation accuracy is coming 75%. So it is doing well on the Parkinson data, but doing slightly not good on the normal for healthy patients. So as you can see here, the training and validation accuracy, the training accuracy is very stably increasing, but the validation accuracy, it is like being after a certain point, it is like memorizing the noise the the general data, instead of generalization. So that I have to work in future according to it. And in loss also, you can see the training loss is very stably decreasing, but in the validation loss, yeah, it is after a certain epoch, it is memorizing the data. So it can be modified in future by model modification or by also like modifying the data set for a better performance over the minority class. And you can also here you can also visualize the attention weights. As you can see, in which time step the attention weights will move. So in which time step the model is focusing more, you can see. Yes, so here we have both the healthy and the Parkinson sample. So in approximately in both from 0 to like 25, in the first it is focusing more, and in the second one you can see it is basically it is like distributing it over the whole time step, but it is peaking in between 0 to 25 only. So yeah, so it distinguishes between the two classes. We can visualize them by attention weights, and we can like also see the handwriting trace via the data. And we can see that in the sample one the tracing was smooth, and in the sample 0 you can see it is like very shaky. So like this we can also visualize the two classes and distinguish which is the healthy one, which is not. So yeah, thank you. That's from my side. If you can ask any questions.
So what is the model complexity? How many parameters are there?
So as I shown you here, approximately like yeah, total trainable parameters are like between 400 to 500K parameters in the whole model. Yes.
Okay. So how do you reduce the overfitting that is happening after
Yes, sir. Initially I did the data augmentation, added the random noise, especially for the minority class, because yes, especially for it only, and then I used the weighted loss function. So to punish the misclassification differently for majority and minority class. So like increase the test accuracy little bit.
So maybe you should try quantization also, and so that we can reduce the model size, so that we can deploy
Yes, sir.
at the
Yes,
device.
so definitely.
Okay, good work.
Yes.
Thank you.
Okay, thank you, sir.
Hello, am I audible, Abbas?
Yes, sir. Yes.
So I'm just asking one question that why you think that class imbalance problem handling is necessary in this problem?
Sir, because of the model learning, sir. Because if you did not handle the class, it will it will not predict the minority class properly. Like it will do well on majority class, but not on the minority class. That's why.
And
So we
what
have to
could be the
change
side
the.
effect of that? What could be the issue with that?
Sorry, sir.
What could be the issue if your model is failed to predict minority class, or we have high minority class misclassification, then what will be the issue?
Sir, as I showed in the confusion matrix, it will that the training accuracy was more. So it was, and in the testing accuracy, we came to know that after a certain epoch, it was like memorizing the training data instead of generalizing it. So that was the main problem, I think.
No, I think it's a medical domain problem. That's why, because we
Yes,
are our target, your model target is to predict the positive class,
yes,
right?
yes,
With high
yes,
accuracy. But
yes.
yes, so it's used is required because to minimize the or enhance the recall value. Thank you. Good
Yes.
work.
Okay.
Thank you.
Thank you.
So I think we're done with the questions. Thank you, Abbas, for taking initiative for such an important problem. And I also believe like your models will be helping many other people soon. So thank you for the presentation. So moving on with our next participant, that is Anushka Jain.
Yes, ma'am.
Yes, Anushka, you can start with the presentation. And I'd like to request all the participants, please try to keep it within the time frame because we have other participants too for the session. A
Is my
gentle
screen
reminder.
visible?
Yes, Anushka, it is.
Okay, so I'm starting. Good morning, everyone. I am Anushka Jain, a BTech student from IIT Indore. So I'm here to present our project titled OnCure, which is a web-based application that uses deep learning to detect and classify brain tumors from MRI images. The goal of our project is to bring AI-powered healthcare tools closer to the general public and doctors alike. So moving to our problem statement, what is the purpose of this model? So brain tumor detection is often a time-consuming and expertise-driven task. Early-stage tumors are especially hard to detect with the naked eye, and in many rural or underdeveloped areas, radiological support is lacking. Our challenge was to solve this problem using deep learning to automate and improve the accuracy of diagnosis. So what is our proposed solution? We have built a deep learning-based web application that detects brain tumors from MRI scans. Users can upload an image and the model instantly predict whether a tumor is present and its type. And our platform is also includes educational sections about symptoms, prevention, and direct links to connect with doctors. Our main proposal is to make a website, but now we have only made the code. We are working on the website. So what are the key components? The solution has three major components. Here's a trained CNN model for brain tumor classification. I have used a pre-trained CNN model, which is VGG16, which is already trained from ImageNet, a transfer learning model, and a user-friendly website interface using Streamlit, and informative sections that guide users, explain symptoms, and connect them to healthcare professionals. Okay, so what is our innovation in this? So what makes our project stand out is the blend of real-time AI prediction and public awareness. We have used a VGG16 model for high accuracy and have integrated educational content and doctors' contact pages, turning a simple diagnostic tool into a comprehensive healthcare assistant. And what are our unique features in this? We have made a doctor page interaction, a user-centric design, which is helpful in both rural areas and underdeveloped areas in which people have lack of information regarding this. Moving to our tech stack. Our tech stack includes MRI image dataset from Kaggle for model training, which I have used MRI brain images from Kaggle dataset, and we have used Python programming and Keras and Dumpy, Pandas, Matplotlib, and Pillow for image rendering. For data and storage, we have used MRI image dataset and local cloud storage. And the web dev part, which is not completed yet, we have used Streamlit now. And for deployment and hosting, we have used GitHub and Streamlit, etc. What is the architecture of a model? So our model, as I've told, that it is for brain tumor detection. And I have used the platform Google Colab for development, training, and testing using GPU acceleration. So our data set is classified into brain tumors, like they have four classes: glioma, meningioma, pituitary, and no tumor. And the data set was split into training, validation, and test sets to ensure the model learned general patterns and not just memorized. So first, moving to image processing. All MRI images is sized to 128 cross 128 pixels for model compatibility. So resizing is important for a good accuracy, and so the model can be trained accurately. And then we have done the normalization 0 to 1 range for faster convergence. And after that, we have applied augmentation, rotation, flipping, zoom. After that, we have used activation function like ReLU and softmax. And the transfer learning model, we have used VG16. So we have used global average pooling 2D flatten layer. And finally, we have used like dense layers with ReLU activation. Wait a minute. And then we have fine-tuned the dense layers with ReLU and softmax activation function. What are our performance metrics? We have trained and our accuracy is 98% and our validation accuracy is 95 to 96%. Our test accuracy is 94%, and we have used the loss function as binary cross entropy, and optimizer is Adam. Moving to next, what is our data visualization? Like our data set that we have taken from Kaggle, which includes this all 4 classes, and it is split into training, validation, and after that we have used this all to train the model. We have showed these images, we have trained them, and after that, with confidence and accuracy, the model has told that it is a no tumor and it is a glioma. And after that, we have make a confusion matrix also to visualize what is true false predictions. And like for example, in this confusion matrix, it is showing well the model classified the different tumor types. Most misclassifications occurred between glioma and meningioma, which often look similar. So we can say that it is working properly. These are the results that our model is showing, that it is glioma, meningioma, and no tumor with confidence of 92, 99, and 98. So it is working effectively. And what is the real world impact of this? Our project is highly scalable. It can be adapted to other diseases like lung cancer. And we have used built-in Python using Flask and Streamlit. And so it is easy to deploy and expand. It supports multi-user access, and we can even integrate features like patient records or multilingual support in the future. What is the social impact in this? It helps in early detection, which increases chances of recovery, and it making diagnosis accessible in rural and undeserved areas. It supports doctors with preliminary analysis, and it educating the public with awareness content. So it is a medical model, so we can say it is good for us. So thank you, and this is our team.
So
Thank you so much for your time, and I would love to answer your questions.
I just wanted to know, have you come up with the demo also? Because you have been using Streamlit and other UI things. So have you come up with that, or you are planning to use those?
No, sir. We have not made the final website, or now only we have done the code part. So
Okay.
finally, we will make the website.
Okay, so thank you, Anushka. It was a really insightful presentation, and your application would surely be benefiting a lot of people. So once again, both of you, thanks to your team for making and working on this particular problem statement. Next, we will be moving with Krunal Parmar. Do we have Krunal Parmar with us?
Hello.
Yes.
Actually, ma'am, Kunal Parmar is not here. I would be presenting on the behalf of him. I'm his teammate.
Okay, sure. So, Rudra.
Yes.
Yes. You can share your screen and start with the presentation, Rudra, please.
Is my screen visible?
Yes, it is.
Okay, so good afternoon to all the participants and judges present over here. I am Rudra Chauhan from Birla Vishwakarma Mahavidyalaya, presenting a project on machine learning using a phishing website detection. Basically, what we have faced a real challenge problem is phishing. What does the phishing that actually mean? Phishing actually means that it is a kind of cyber attack where the attackers trick individuals into relieving sensitive information such as username, password, credit cards, number, or personal data by pretending to be trustworthy, like a bank company or government agency via email messages or fake website. So what we have done over here is we have yes, the problem we are facing is rising threat landscape. Means every day by day the threats are increasing, more phishing websites are involved, and the attackers are attacking to the common people. And there is a significant there is a significant problem that is this a website trustful or not. Another is according to 2003, 4.45 million data have been breached evasion of traditional security. Social engineering techniques effectively bypass traditional security measures, making it challenging for the conventional system to detect and prevent sophisticated phishing. Broad consequence beyond the financial logics. Here the problem we are facing is to damage for the affected entities, eroding trust and causing long-term harm. So what was our motivation? Currently, we are not having any of the what you say web extension or say web that detects that the given website is a what you say is a phishing website or a real website. So we have built a model in which we would be detecting that it is a phishing website or not a phishing website. So what it would give? What it would give by enabling real-time detection. Phishing guard significantly prevents financial losses and safeguard personal and sensitive data from the attackers. Market demand. There is a huge demand in the cybersecurity solution, making this project highly relevant and commercially scalable in today's digital economy. Another is existing phishing detection. Currently, yeah, when we were finding the solutions for the program, we didn't find any of the app or say web app or say extension which real-timely detect that the phishing website is a real website or a phishing website. So what we have applied here machine learning approach for the detection of it. And the data set, we have taken a data set from my college senior in which there are 10,000 website data, out of which 5,000 were real website and 5,000 were phishing website. So what we are it is a rich feature data set in which includes URLs such as LAN, special character, IP addresses, and many more. Content and domain insights. Content features include specific keywords and external domain links, while domain features leverage whose information and DNS record. For instance, URL can be longer than 50 characters. It may be contain some of the keyword that might not contain in your website. And third is the model architecture. We have first taken the input a URL from the HTML. Then we have two hidden layers, one with 64 and 32 neurons, employing ReLU activation for non-linearity and effective gradient propagation, and the output layer with the activation sigmoid activation for phasing probability 0 to 1. Basically, our model was having total 10,000 columns and 49 rows, including one row which would tell us that it is a phishing website or not a phishing website, which is labeled as class label. So first of all, we had trained our model and we see that there is no proper accuracy. So what we had done was we had plotted the heat map, and from the heat map, we have taken some of the values which would give us the high accuracy for detecting the website. Training and strategy hyperparameters. First, 80% of training and 20% of testing. And for optimization, we have used Adam optimization with learning rate of 0.01 and batch size 32 and 111 approaches to ensure that there is less accuracy. And early stopping 10 approaches for monitoring validation loss to hurt training when performance plateau saves computational resource. So this is the heat map of the core. Basically, we have plotted the heat map for the correlation of the what you say that the phishing website is not, and out of that we have figured out that only 11 were the main what you say correlations which would detect that the given website is a phishing website or not. This is the heat map. And here is our model training accuracy. First of all, we had used less trainable parameters, and after that we have increased the trainable parameters by increasing the dense layer from 64 to 256. And what we are first of all, what challenges we have faced? We have find a data set which was not available publicly, so we have taken it from our college senior who was working in the IT, especially in cyber security. And then we have searched that what can be a new innovative solution. There is a thread that this is website or not, but real time it doesn't tell that it was a fake website or not. So what we are aiming that we would build a Chrome extension, which when you would click on the website, it would directly tell that yes, it is a phishing website, so don't move forward or stop over that, or just it would not open the Chrome website. And feature selection, identifying the most impactful feature for accurate detection was challenging, as already told that 40, 49, 49, 48 columns were there, and we have figured out only 12, 11 to 12 columns, which were the main for detecting the phishing website. And what is the conclusion? Our fish guard, we would be building a web app in which just you can paste the URL and you would find that it is a phishing website or not. On the upper layer, we would be also building a Chrome extension, which when it would be installed on the Chrome, it would be directly telling that you should go to that website or not go to that website. And that's all our project was. Thank you, Malaysia. Any question? Is my voice audible?
Yes, Rudra, you're audible. Do we have any questions from the panelists? Okay. So I
Audible?
believe, yes, sir, you are.
You said that the data set you have collected from your institute means from where you have collected data set?
It is from our college senior Billa Vishwakarma Mahavidyalaya.
So means you have means it was labeled data set or you have labeled by
No,
yourself?
it was a labeled data set we have got from our seniors. Basically, they were working on this project, but what they happened, they do not get the proper accuracy. Therefore, we have taken that project and we are working to build a Chrome extension.
Okay, thank you.
Okay, thank you, sir.
So thank you, Rudra, for this insightful presentation. And now we will be moving with our next participant, that is Atul S. Do we have with us Atul S, or if Atul S is working with the participant or partner, they can to present. Okay, so I believe they might be taking some time. Let's move on with our next participant, that is Divyansh Dhawan.
Yes, I'm audible.
Yes, Divyansh, you are. Please share your screen and start your presentation.
Right, so is it visible?
It is visible.
I'll try. Yeah, so basically, good afternoon, everyone. Today I'm Divyansh Dhawan, BTech undergrad from Manipal University, Jaipur. And today I will be presenting my project question answering using RAG system. This is my capstone project from that I made for deep learning semester. Yeah, so basically what the problem statement tells about is that the core problem we address is the need for a question answering system that can provide accurate and contextually relevant answers. That is missing in nowadays. Traditional models either rely solely on pre-trained knowledge or simple retrieval, but they often miss recent or domain-specific information. So by leveraging RAG, we combined retrieval from a custom knowledge base with generative capabilities, grounding answers in up-to-date authoritative sources and reducing hallucinations. Right. So basically, my motivation and relevance behind it was that unstructured data in nowadays is just increasing every day. And using RAG, it combines retrieval and generation, improving answer quality for real-world applications like chatbot, search, and support. So it is a very important thing in nowadays that can help many people. So the literature review talks about that retrieval augmented generation. It combines neural retrievers. For example, we studied about it in our course to vector databases and like embeddings with language generators for improved QN. So the key tools used in my project were Facebook AI similarity search, that stands for FAISS. So it efficiently matches the similar contextual, basically semantic meaning of the lines, and sentence transformers are used for text embeddings. It embeds the lines. And then I used Gradio for interactive web interfaces. And we can use for further development LangChain, Haystack, and OpenAI APIs for advanced RAG implementations. The dataset description, if I talk about it, so basically I used a sample knowledge base, which is basically I made a knowledge base for myself, a custom knowledge base, because I made this project on a small scale. So I used a few short documents on deep learning and related. By documents, I mean like lines or paragraphs. And so, for example, this is the example. Um, for example, neural network, convolution network, transfer learning, and many more. There were explainable AI, everything we studied about in this course. And then the model architecture, it comprises of three main components. Document store, basically it stores all the documents as a knowledge base. Retriever, it uses sentence transformers, embeddings, plus Facebook AI search, similarity search for semantic search. And generator, basically in large language models, generator is used for example like ChatGPT and other AI tools. But this is a very basic model. So in the use of generator, I've used the context that I was provided with in the knowledge base to be written in the same way in the answer. And then the workflow is in the form where first we encode documents into vectors, and the documents and queries. And then we retrieve top k relevant documents for a query, for the query that we were given. And then we generate the answer using the context. So training strategy and hyperparameters, I use the embedding model all mini LM L6V2. That is a variant of BERT. It has a default dimensional vector of 384 dimensions. And then I use the vector index FAISS, index flat L2 for fast similarity search, where index flat means basically flattened array, and L2 means the distance. So retrieval, yeah, right. So like I talked about top K retrieval process. So top three documents per query are retrieved, and since it is a very basic project I made, so I did no fine tuning. It used a pre-trained embedding model for simplicity and speed. Yeah, it is a fast model. So document addition, dynamic support users approach. And then the result and evaluation, basically, when I tested it, it gave me a relevant answer when I search for questions like what is explainable AI, how these are the examples. Like I asked what is explainable AI based on the available information, it gives me the correct answer. And then it also gives me the top key answers. Then I asked for multiple questions. What are the applications of CNN? How does RSG work? So that's like it. And basically, what challenges were faced are basically I had very limited context. I do have a scope to add documents, but to make it on a large scale, it needs to be done in a bigger way. So I had very limited context, and similarly, I had a like small knowledge base, and there was no deep generation. Like does not use large generator models, like I said, and scalability, FAISS, and embedding size limit for very large datasets. So conclusion and future work are like achievements. I built the functional RG, and future enhancements can be that it can be integrated with a large language model for better answer generation, and we can add metadata and advanced filtering, implement de-ranking and chunking for longer documents, right? And explore frameworks like LangChain for production-ready solutions. These were my references. Chris McCormick AI. It's a YouTube channel. It helped me a lot. And the documentation and RSG paper. Thank you. I would love to answer some questions.
So how did you generate the knowledge graph? Did you use the triplets and then followed by graphs?
So can you please repeat?
How did you generate knowledge graph here?
Yeah.
Each sentence you converted to triplets and triplets are combined to form a graph.
No. Basically, I used knowledge base and vector embeddings and the Facebook AI search, similarity search to make the knowledge graph. Are you talking about knowledge base?
Yeah, knowledge graph. You are prompting knowledge graph, right? So knowledge, given a sentence, we have to extract the object, subject, and predicate, and then each of the sentences are processed to get a bigger knowledge graph, and then you put graph embedding, and then you extract information. That's a basic pipeline from scratch. Maybe you are using other libraries, so intermediate steps
Yeah.
are you are not familiar.
Yeah, actually, I think so. Basically, what I did was I used sentence transformers. I used for vector embeddings, I used FAISS, and for generation, basically, I just used for retrieval. When a user asks question, it is embedded, and the similarity search happens in FAISS, and according to that, my answer is the answer is
Okay, I
provided.
understood. So you do with more basic approaches, okay? Given sentence, how to extract the information using subject, object, predicate. Then you create a knowledge graph rather than using sentence transformer, so that you have a little more flexibility. Okay, then.
Oh, all right.
Okay.
Right, right.
Thank you.
Thank you so much.
Thank you, Divyansh.
Thank you so much.
I hope the insights will help you to make your project better in future. So next we have with us R. Donna. Pardon me if I'm
Yes.
pronouncing it wrong. So yes, please can you share your screen and start with the presentation?
Okay. So good afternoon, everyone. I am Donna R, currently pursuing BSc at Ravi University, Bangalore. And today I'll be presenting my project on pneumonia detection using chest X-rays. Yes, so this is the capstone project I've done as part of this course. So the problem statement is pneumonia is a lung infection that, if left untreated, can be fatal. So the traditional diagnosis relies on manual interpretation of chest X-rays by radiologists, a process that can be little slow and sometimes error-prone. So this project aims to automate the pneumonia detection using deep learning and improvise the speed and accuracy in the medical diagnosis. So the motivation and relevance. Pneumonia affects around 2.5 million people annually, especially children under 5. So the early detection is crucial to reduce the fatalities. In regions with limited access to medical professionals, this AI-powered tool can be a life-saving role. So this project also demonstrates the real-world impact of the machine learning in healthcare. So, for the literature survey from the videos and the papers that I've reviewed, I can say that the convolution neural network is highly effective for medical images and analysis. I prefer transfer learning, which is especially mobile net, which is lightweight and powerful model. It offers high accuracy and is efficient on devices with limited resources, making it ideal for real world application. So for the data set, I used the open source dataset that is from Paul Money's chest X-rays images that is available in Kaggle. So it has around 5,000 training images, 600 validation, and 600 for testing. The two classes were normal and pneumonia, and I had to resize the images to 224. And then there was a huge imbalance in the data set that was there in Kaggle. So for the model architecture, I had chosen two models. I tried two models. One is custom CNN. I tried CNN with multiple layers, but then the accuracy was pretty low. So I went about the basic CNN architecture. So then I tried MobileNet. That is a transfer learning model with the base frozen, and the custom classification layer was later on is added as well. So the CNN was simpler. The mobile net showed better accuracy and the feature extraction and good feature extraction capabilities. So training strategy is first I had to normalize the images and augment and use augmentation techniques like rotating, shifting, and zoom. And for optimizer, I used Adam, and the learning rate was 0.001, and the loss function being binary cross entropy. For CNN, I used 10 epochs, and for mobile net, 5 epochs was enough to get the desired accuracy. With the different experiments, these were the parameters I found was helpful in getting an improved performance. So for the results and evaluation, CNN achieved around 86% test accuracy, but I think it struggled a little bit with the generalization, whereas MobileNet achieved about 88% accuracy on the test data. So here you can see how it is going about with the precision recall and F1 scores as my evaluation metrics. So I can say that the transfer learning has reduced the false negatives and giving about a good uh, prediction even for normal data, which was what suffering with imbalance, which is what was suffering with imbalance. So the number of correct predictions that the mobile net did was around 549 images, and the incorrect was 75 images that it predicted wrongly. Uh, So the challenges I faced was there was imbalance at the earlier trials, and there was a little bit overfitting in CNN. I There was model, and there I had resource problems as well. But the collab was little bit suffering because of the huge data set. And for concluding this, I can say that the transfer learning proved more efficient than traditional CNN, and it the project shows that how pre-trained models can aid in medical diagnostics. So the future work can be to use to make the model more explainable, and to use other architectures like DenseNet and ResNet 50. And I can also try and use ensemble modeling to improve the reliability of the project. So references, I used the data set, and then I just went about knowing how to go about this project through some reference papers and try to apply the knowledge base I got from the summer school. So I also tried to implement a Streamlit application to just demonstrate how it can be used in real life. So suppose I input an image. So this is a normal lung footage. Yeah, it shows that this footage is a normal lung structure, and then to show its pneumonia.
अविनाश भी गए, समा भी गए, साक्षी भी गए, अब अपन नहीं जा सकते.
Yeah, so here you can see that this is a pneumonia X-ray scan. So that is how I went about this project. Any questions?
So thanks a lot, Nona. It was a really good presentation, and it was solving a really crucial problem statement. So thank you once again.
Thank you.
So we will be moving with our next participant, that is Durgesh Singh Kaur.
Am I audible?
Yes, you are.
Hello everyone, my name is Durgesh Singh, and our project is all about the ASL character recognition. So introduction. So we use ASL. ASL is a visual language used by deaf and hard of hearing community, and it's an automatic ASL recognition help bridge the communication gap. And this project uses deep learning to recognize ASL alphabet from images. And
Durgesh, you are not audible clearly.
Hello.
Mr. Durgesh, you are not audible clearly. Please speak louder.
Hello. Now audible. Hello.
Yes.
Yes, you are.
So, what was the problem and motivation? So, communication barrier affect over 70 million deaf individuals worldwide, and lack of any tech app limit social and educational opportunities. And our goal was to develop an automated ASL recognition system, which has 95% over 95% accuracy to bridge this gap and utilize modern AI framework to robust and scalable solutions. And project objectives and develop a robust real-time ASL recognition system to bridge communication gap and ensure accessibility through a user-friendly interface and open source deployment. Leverage state-of-art deep learning and computer vision techniques. And this is whole technology that we use in our model. The deep learning frameworks that we use, TensorFlow and Keras for model development and training. And for training transfer learning models, we use VGG16 Why we use this? Because it has an proven performance in image classification task. And for hand detection, we use media pipe. So media pipe is very important for hand detection in real time and landmark extraction. And for deployment purpose, we use Hugging Face species for public and cloud-based access. And also we used OpenCV for image processing and scikit-learn for evaluation metrics. So these are the whole data set that is available on the internet.
इन्होंने selected sheet भेजी
Alphabet, which has 29 classes, 87,000 of samples. So that is the data set that we use. This contains 29 classes, A to Z plus delete, nothing, and space. And we resize images from 200 cross 200 to 224 for compatibility and pre-trained model. And we normalize pixel values for stable training, and then one hot encode. We used one hot encoding label for the multi-class classification. We split it data 80% for the training and 20% for the validation purpose. So here we can see that ASL dataset have an equal dataset over 29 classes. And we use data augmentation. So what is data augmentation? It is used for the to model, introduce the we can change brightness, and as we use our model, then in a real time. So it can give us a problem uh, like brightness as we change our brightness or flip our hand. So accuracy will reduce, right? So for that we use data augmentation. And in this, we use random rotation, width and height shift, shear zoom, and horizontal flip, and also brightness adjustment and real-time augmentation with Keras and image data generator. And impact was make the model reverse to variation in hand position, lighting, and background. And we used our VGG16 model. And first we did transfer learning. In transfer learning process, we use a pre-trained model. So we use this, and for weights, we use MedNet. And then for the last layer, we use this custom head. And then I did 2 times fine tuning. So fine tuning process, what we did, we unfreeze the last of the layers for model learn more to increase our accuracy of the model. So we did 2 times fine tuning. And first time I did unfreeze the four layers, and second time I unfreezed 8 layers. And then we use media pipe and use for the real-time hand landmark detection. And it improved hand region localization and reduced the background noise. So, and then enhanced input and quality for the classifier. Then we use augmentation that we discussed before. In callbacks, early stopping, and reduce on played out. And batch size in the first fine tuning we use 34, and second we use 64. And in coaches we use 15 coaches, first in 10 and second 15. Fine tuning, and as we discussed before, these unfroze layers. And we use hyperparameter tuning for learning rate, batch size, and augmentation range. And this reduce the overfitting. For the real-time application, live webcam input processed via media pipe and pre-process and fed to fine-tune VGG16 model, and prediction displayed on the web app UI. And deployment, for deployment purpose, we use Hugging Face and Streamlit app for the friendly interface. So Streamlit is in why I use Streamlit, because it is very we can deploy very fast on this platform. So that's why I use this. So that is whole website. prediction was F, and that's why we use the media pipe over here. There you can see that, and the confidence level of 71%. The confidence level is 72%. And then performance. So it gave us a 96% of the performance after 2 rounds. So still I'm improving this model. I'm again, after this PPT, I will again fine tune this model to increase the accuracy. And that's a training curve. And accuracy improved steadily, loss decreased and stayed, right? So as we can see in this plot, our accuracy is increasing and loss is decreasing. The challenges that I faced in this making this model. So some of the ASL sign have a more images than others, causing model bias and lower the accuracy. And then real world variability. So that's a very huge challenge. So challenges like as we change our lighting and background, hand size, so result are keep changing. So that's a problem. And similar gadget. So that is also a problem. Certain as ASL letter look visually similar, like M and N, T and E, so leading to frequent misclassification. And also, we face the overfitting risk. So model may perform well on training data, but fail on the new users or unseen environment. As we improve this in data augmentation, but overfitting is always there. And the deployment constraints. So achieving a real-time performance with a high accuracy on the standard hardware isn't very challenging. So that was challenges, all about challenges. And for ethical privacy and consideration, no webcam data was stored or transmitted. No, so user consent is required for the camera access, and one source code for the transcripts. In conclusion, we study successfully implemented CNN and tensor flow model for the ESL alphabet recognition. And however, certain letters pose challenges highlighting the need for the refining the model architecture and data selection. Moving forward, incorporation and landmark data would enhance the model precision and the resilience by providing detail and positioning and information. So, thank you so much.
Do we have any questions from the panel? Okay, so thank you, Durgesh. Acknowledging the communication gap between people is really important, even for Indian Sign Language and American Sign Language. So this project is really amazing. Thank you. So we will be moving with our next participant. That is Meghna Gade.
Good afternoon, ma'am.
Very good afternoon, Meghna. Please share your screen and you can start with your presentation.
Ma'am, is my screen visible? Hello? Hello?
Yes, it's visible, and make a presentation within limited time, that is 10 minutes. Huh?
Okay, sir. My project is air quality prediction using time series. I'm BTech student pursuing my BTech in IIIT Jabalpur. I have taken my dataset from Kaggle site. My dataset is of Beijing. It has data about it has data of air parameters like pollutants and meteorological data. These are the features which are in my dataset. In my dataset, there are 12 files, means it is about 12 stations in the Beijing. I have combined all these stations data into one data frame. Basically, my goal is to predict the air quality for the whole Beijing city. So that's why I have combined all these stations data into one data frame. And next, I have done my data pre-processing by using these steps. Firstly, I have in a related data set, missing values are very common. So first we have to fill these missing values. I have done this based on two approaches. If the missing values are less than 8 hours, then I have done that using linear interpolation, and if they are greater than 8 hours, then I have done that by averaging the same hour value from previous day and the next day by taking this average. I have taken this approach from the article which I took reference for doing this project. And next, I have dropped some features which don't which have 50% missing values. And I have mapped my wind direction. Basically, wind direction is given like north, east, and like that, like string values. But I have taken degrees, and I have mapped my wind direction and hours into sine and cosine values. And at the last, I have normalized these features using min-max scalar. And next, I have done feature selection. Basically, I have done feature selection using a decision tree classifier, as it has 12 stations data. So I'm having almost 3 lakh rows. So that's why I have decreased the features for my model's efficiency. Basically, I have taken only top 3 features which play importance for the exceedance of the pollutant. So I have done this using decision tree classifier. I have plotted for each pollutant and majorly taken the top 3 features which play major role for exceedance of that pollutant. And next, I have used ARIMA model. uh, I have not done my whole project based on the ARIMA model. I have just used ARIMA model for a feature for residual extraction, which can be used for my further LSTM model. But ARIMA is a model which can be used for forecasting future values. It is used to uh, capture trends. ARIMA, I have done some research about ARIMA. Basically, ARIMA is done by using 3 parameters. Those are autoregressive, integrated, and moving average. Autoregressive part tells us that the predicted value can be known from the previous error values, and the integrated part uh, says that we can know the predicted value by calculating the errors from the actual values. We can calculate errors, means residuals, by doing subtraction from predicted value and actual value. And moving average part tells us that we can know the predictions from these errors. Means we can know the trends, or if there are any patterns from these errors, so we can learn patterns from these errors. So that's why I have used ARIMA model to extract residuals feature. And then this is my training strategy. I have used time steps. Time steps means uh, my I am giving in my model I have given 24 time steps. Means my model will predict. My model will consider last 24 hours data for prediction of next value. And I have done train test split, like 80% for train and 20% for testing. And for scaling, I have used a standard scaler. But I have used early stopping because to overcome overfitting. That's why I have used early stopping. Means I have took patients equal to 15, because if for 15 epochs there is no change in validation loss, then my model will stop the training and take the best metrics values from the last epoch. And next, this is my model architecture. In input, I have taken the 24, means here time steps, as I have told in the training strategy. And features, these are the input features. And next, I have used a convolutional layer uh, to extract features. And next, I have used max pooling. I have to convolution layer using padding to take same to remain the same dimensionality. And for max, I have used max pooling using pool size 2 to decrease the spatial dimension. And then I have used LSTM. Basically, LSTM model is the model came from RNN architecture. I have chosen LSTM because LSTM is very good for sequential data. My project is based on time series, that's why I have used LSTM. I can choose RNN also, but in RNN we have a problem of vanishing gradients. But LSTM can overcome this problem. That's why I have chosen LSTM. And there is an advantage of because of LSTM. LSTM predicts the future values by keeping the previous patterns uh, from the before layer. That's why I have chosen LSTM. And then I have used dropout layer. To randomly drop some neurons to overcome overfitting. And then I have used fully connected layer for the output at the last layer. These are the hyperparameters. I have used loss function, mean square error, and for optimizer, Adam optimizer. And I have done normalization, used the min-max scaler. For model evaluation, I have used these four metrics: MSE, MAE, RMSE, and R square. These are the values I have obtained from my model training. And we can see R square should be almost equal to 1. R square should be greater, from which we can tell that our model is trained well. So R square should be higher. This is one of my output. I have predicted the concentrations for each pollutant in my data set, but I have kept one plot in my slide. This is the plot of NO2 pollutant. Here, blue lines represent the actual concentration, and orange line represents the predicted concentration. As we can see, some parts of the blue lines, my model has predicted very, very accurately, but it missed some points. So that's why we are able to see some of the blue points at some places. And at the last, I have calculated the air quality index also. Basically, air quality index is a value which tells the air quality according to that pollutant. We calculate air quality index for each pollutant. This is the formula used for the calculation of air quality. For this formula, we use standard values. I have taken the standard values from CPCP Association. I have taken Indian standards. This association provides us threshold values for each pollutant and averaging periods. Threshold values means these are the safe limit values. If the concentration exceeds from this safe limit, that means it will be harmful for us. That air will be harmful for us. And averaging periods means there will be specific time periods in which we can calculate the averages. These are the I have mentioned the average time also for each pollutant. These are the values I have taken for the calculation of AQI and my for ARIMA also, and for feature importance also. These are the standard values I have taken from the CPCB Association site. And next, this is the uh, plotted graph of AQI. In this, I have plotted for all pollutants in only one graph. Here we can see at the background I have used colors which says that if air quality index is more than that range, then it will be severe or very poor or satisfactory. That's why I use the colors. And for each pollutant, we can see AQI plotted graph. This I have plotted this AQI graph from the test series, on which I have trained the model. And in this, firstly, I also tried to predict for each station. For this model, I have combined the all data of all 12 stations, but I have tried to predict the pollutants for with respect to each station, but I was unable to do that. In future, I'm thinking to work on that. And I have also faced challenges on overfitting and arima residuals. Mm. Thank you, ma'am.
Any questions?
Ishita, Ipsit, right? What's your name?
Meghna, sir.
Oh, sorry, Meghna, yes.
Yes, sir.
So, like lots of model you have studied here.
Yes,
Do you
sir.
think any other model can be applicable in this data set?
We can do this solely based on ARIMA also, sir, and I can use attention layers in the
Okay, means you can use the the transformer.
TM to overcome the vanishing gradient.
Okay, thank you.
And we can do this on ARIMA also. Thank you, sir.
Thank you, Meghna. So now let's move with our next participant. Do we have Ipsit Singh with us? Ipsit Singh. Pardon me if I'm pronouncing it wrong. Ipsit Singh. Okay. So now moving on with our next participant, that is Juhi Faridi.
Yeah, okay, I'll share my screen once again. Is my presentation visible?
Yes, Juhi, it is. You can continue, please.
Okay. Good afternoon, everyone present in the meeting. I'm Juhi Faridi, and the topic of my Capstone Project presentation is EEG time series classification for schizophrenia, a study of 1D CNN and 2D CNN approaches. Sorry. So this is the presentation outline. I'll be taking up the problem statement, motivation, literature review, dataset description, model, training strategy, hyperparameters, results evaluations, followed by conclusion and references. So the problem statement is like schizophrenia is a severe mental disorder that lacks efficient non-invasive diagnostic tools in early stages. With the help of EEG signals, which records the brain's electrical activity, it was promising for identifying neurological patterns associated with schizophrenia. So this project addresses the challenge of earlier non-invasive schizophrenia detection by analyzing the EEG signals using the deep learning models. Specifically, it evaluates and compares the performance of 1D CNN and 2D CNN architecture in terms of classification accuracy, memory usage, number of trainable parameters, and other metrics as well. The ultimate goal is to support the early diagnosis and enhance clinical decision making through effective brain signal analysis. So, as I already said, that schizophrenia affects over 24 million people globally, often leading to long-term disability if not diagnosed early. So the early stage diagnosis is challenging due to the subjective nature of symptoms and lack of accessible clinical tools. Subjective nature basically means the doctor depends upon what the patient is reporting, like the problems of hallucinations or the memory disorders. So EEG is a non-invasive and a cost-effective technique that captures the brain activity and shows promise for identifying neurological abnormalities, which helps detecting this disease way earlier, which is usually detected in very late stages of life. So deep learning can automatically extract complex patterns from EEG signals, improving the accuracy and speed of the diagnosis. And hence this project contributes towards building AI-assisted tools that can support clinicians in early detection of schizophrenia using brain signals. So as a for this like for the Capstone project, I had to choose a problem. So I did some literature review, and I found that there's a recent paper by Latridge et al. Published in 2024. And so they reported a 10-layer 1D CNN architecture, which achieved a mean accuracy of 99% using 10-fold cross-validation on the same data set that I have used in my problem. The model reported by the authors used convolutional layers, max pooling, global average pooling, dropouts, fully connected layers, similar to the baseline CNN architecture that I have used. And this also validates that the deep learning can autonomously extract features from raw EEG signals without manual feature engineering. And this project further expands on this by comparing 1D and 2D CNN models for improved temporal and energy-aware modeling. This is the proposed methodology used by me. First, I have used the data set, which is the EEG signals in the 19 channels form using the 1020 format. Then I have performed the band pass filtering, choosing the pass band between the range of 0.5 Hertz to 45 Hertz, because this is the main region or the filtering region which has been reported to affect the schizophrenic patients. Then I have done the windowing using the size of 5 seconds and overlapping of 2 seconds. Further use the min-max normalizations, and then the two CNN models, 1D and the 2D, and then the classification networks are further classified the patients into the subjects into the patients and the healthy persons. So this is the dataset description. I have used it from the Kaggle, where there were 14 healthy subjects and 14 patients with paranoid schizophrenia, and the 1020 system with the 19 channels using the sampling rate of 250 Hertz with the reference electrode placed between this FZ and CZ. So this is a 1D CNN architecture where I have used the convolutional layer using the ReLU activation function followed by batch normalization, max pooling of 2 and dropout of 0.3. Then again another layer with 1D convolutional batch normalization, max pooling of 2, dropout of 0.3. Further flattening and the dense layer with ReLU activation and a dropout of 0.5, and then another dense layer with a sigmoid activation for final classification. And the total parameters, trainable parameters and the non-trainable parameters have been reported here. This is the 2D CNN model architecture where there are 3 layers of convolutional and max pooling, and the blocks have been repeated 3 times. Then further the after the third max pooling layer, I flattened, used the dense, then the dropout of 0.5, and then again the dense for final classification. And the parameters have been reported here. Training strategy and parameters are for both the architectures. A loss function is binary cross entropy loss. Adam optimizer has been used, and the learning rate was 0.001. Batch size for 1D was 64, while for 2D I've taken 32. A number of epochs with early stopping has been taken, 50 for 1D and 25 for 2D with a patient's level of 10. And I found that the best model saved for 1D was around 22 epochs, and for 2D it was 21 epochs. And the train validation and test plate ratio was 70:10:20. So these are the results for the 1D and the 2D CNN. We can see the 2D CNN has reported slightly higher accuracy, and all the other metrics are almost similar. And the parameters have also been compared, which shows that the 2D CNN is taking like almost double the space and double the parameters. Here there are no, we have seen trainable parameters, and here there are no trainable parameters because I haven't used any batch normalizations in the 2D CNS. So every parameter is being updated. And here some of the parameters are not updated, so they are the non-trainable parameters. There was one more problem that I saw in the 1D CNN was like, this is, I think, the accuracy as I was training multiple times, the accuracy was changing like from, it was varying usually, but this was not the case on the 2D CNN. So I thought to apply the K-fold cross-validation technique, but because of time constraints, I couldn't. So yes, there was some problem in the 1D CNN. And while the 2D CNN was giving much better results and almost consistent results, this is the confusion matrix this is for 1D CNN and this is for 2D CNN. Here we can see there's a slight class imbalance if we add the total number of subjects. So, and the final discussion is like why we have used the 1D CNN and the 2D CNN is here we can see in the 1D CNN the main characteristics that is being exploited is the temporal relationship. While in the 2D CNN, the filters or the windowing is happening in the horizontal as well as in the vertical direction. Now, why this is giving better results is because along with the temporal relationship, the electrodes that are being placed adjacent to each other are also related. So I think here the spatial as well as temporal relationship both are being exploited, while here only temporal relationship is being exploited. So this can be one of the reasons why the 2D CNN is giving much better and consistent results as compared to the 1D CNN. The challenges faced were the training and the testing of deep learning models. 2D was constrained by limited GPU resources, and because of this, I was not able to train it for LSTM, although I have written the code for LSTM as well. But after one epoch, it wasn't training, and there was slight class imbalance, for which I think various class imbalancing techniques like introducing noise and all that can be introduced. And in the yesterday's lecture, I also learned about one more technique that if this class imbalance, we can even use GANs to produce more classes. So I think maybe in the future, I'll be exploring that as well. So this is the conclusion and future work. The project successfully implemented and compared 1D CNN and 2D CNN model for non-invasive schizophrenia detection using EEG time series data. And the comparison was based on key metrics, accuracy, trainable parameters, memory usage. 2D model gave higher accuracy at the cost of increased complexity and resource consumption, while 1D CNN was more lightweight but slightly less accurate. So, since I'm a beginner in this field and my background is electronics, circuits and system design, and 6 months before I was just working on cadence. So I think I'll be exploring SNNs in the future. That's why I took this time series problem specifically for this project. So I'll be exploring it for SNNs. And since I found that explainable AI is something that is very relevant in the medical domain, so I'll be deploying this in the future. And also I'll be, because I'm interested in exploring spiking neural networks, so I'll be exploring the LSTM and RNN techniques as well. So these are the few future works that I plan to implement. These are the references from where I have taken the data set and the reference paper and all. These are the links to my codes. And finally, I would like to thank IIITDM Jabalpur for organizing this first summer school on deep learning, because as I already said, I am a beginner in this field. And this summer school just came to me at the right time. And I would like to thank the speakers and the mentors for constantly engaging the sections and constantly serving my dogs all throughout the summer school. Thank you so much. And this summer school has benefited me so much that I just can't explain it in words. And this is just a small token of appreciation for this. Thank you so much. Thank you.
Thank you, Jogi. So do we have any questions from panelists? Okay, so I think that the explanation was well enough that we do not have any questions. So let's move forward. Thanks a lot. Your presentation was really insightful and clearly explained. So thank you once again. So we would be moving with our next participant now, that is Khushi Pathak.
Yes.
Yes. Khushi, can you please share your screen?
Hello. Hello. Are we audible?
Yes,
Are
yes,
we audible and
Khushi.
visible?
Yes, your presentation is visible and you both are audible. You can move forward with it.
Okay. Hello, everyone. I, Khushi Pathak, and my teammate Kaushik Shaw. Here we are present to present our presentation on the project MythBird. By the name MythBird, you must be thinking what it is, why its name is MythBird. So we have issues like misinformation is rampant online. People delay proper treatments and trust the false remedies and develop harmful beliefs. The gap is that standard AIs as well as Google sometimes provide the answers that lack the depth or the concept. The solution to this is our pipeline, which combines classification, retrieval, and generation to provide accurate, context rich answers, helping people to make informed about the health discussions.
The motivation and the relevance of this project in India is huge. A 2021 study, and we all have noticed it in the time of COVID that there is a lot of misinformation regarding the COVID vaccine going around. There was myth around it like the vaccine sterilizes us or make it something. So that affected a lot on how the vaccine should have affected, should have affected in a more better way because people were reluctant of getting vaccinated because of the misinformation that was spreading all around. And Indian household, it is also common that people just believe in the remedies that they saw on some like social media or some sites, and they even though the children they show the necessary required documents about it, but still they don't believe, and they still believe on the information that they got from some social media. So that is the relevance of this project. And the literature review of it, like what we've used in this project. The first thing is our project is a combination of three things. That is one classifier, one retrieving augmented generation. We have a retrieval model. We have a generating model. So for the classification, we use PubMedBert. We could have used any of these three, like BioBert, ClinicalBert, and but we use PubMedBert, which is previously trained for the medical data only. We fine-tuned it for the three-level classification. We used RAG for the augmented and generation part, T5 model for embeddings. We use FIRES database for fast retrieval, SciFact database for the classification training part, and that is all about the literature review.
Moving with the dataset description, here we have our custom dataset that is 100 manually labeled health myths. Here we have classified it according to three: 0 for myth, 1 for not myth, 2 for inconclusive. Then we have took the SciFact claims, which is 1,409 claim from the SciFact that was mapped into three labeled formats: myth, not myth, and inconclusive. Then synthetic data. 100 additional messages generated to balance these classes. Then we have took the SciFact corpus, which is 5,183 scientific abstracts were used for retrieval in this model. Moving with the model architecture. Here we have a classifier, retriever, and a generator. In classifier, we have PubMedBird, which was fine-tuned to three label held in claim classification that whether our claim is a myth, it is not a myth, or it is inconclusive. Then in retriever part, we have a FIES plus E5 embedding for retrieval of conceptual relevant documents. In generator, we have a Llama 370B GOR KPI to produce evidence backend explanation. The workflow of this model is as follows. First, the PubMedBird classifies the claim. Then the files find out the top three relevant documents. Then using the Llama 370, we get the explanation based on the claim and the retrieved documents.
Now talking about the training strategy and the hyperparameters that we use in the training. So we trained the model for 4 epochs with a batch size of 16. The epochs are less because of the GPU capabilities that we had. We were using Google Colab, and we used Adam Optimizer for optimizing the data. Then we set our learning rate to 2 to the power minus 5, and we use gradient accumulation. Okay, the dataset that we had from SciFact and the synthetic dataset that we generated from the Grow KPI for the same, we used 80% of that for training purpose, and that for testing we used the 20%, which was REST. And we used RAG setup V5 that we already talked about. The environment was Google Colab, and the versions of the particular like libraries that we use, the PyTorch and the Transformer, is mentioned here. Now the results part.
The result and evaluation. In the classifier accuracy, we have achieved about 89 0.3% accuracy on the validation set by combining the SciFact and custom label data. In precision recall per class, as we have told about the myth, not myth, and inconclusive, we have divided according to the precision and recall. In the RAG retrieval effectiveness, we have a top three retrieved documents that we are fetching to get 85% of the claims. Then the explanation quality. It generated an explanation which was concise, about 100 to 150 words, and it was context rich and backed by retrieval of the document. Here we can take an example as such. We have a claim, vaccine contains microchip. The classification is it gives as a myth and confidence of 0.95%. The explanation it gives is based on multiple peer-reviewed studies, which was the statement from WHO CDC that vaccine do not contain the microchip. This myth likely stems from misinformation which has been circulated all over the web and social media. Here we can see the classification model is fine-tuned as we have epoch, then training losses, validation losses, accuracy, precision, and recall, and the model output. As I have already mentioned, the model output we have given it is in a format. It will tell the claim, then it will show the classification, whether it is a myth, not a myth, or inconclusive, and then it will give an explanation based on the retrieval of the documents.
Now talking about the challenges we faced, obviously the making the model was not easy because there was a scarcity of data for the training of the classifier because there are not much dataset presents which are labeled on the three-level dataset that we wanted to use, that is myth, not myth, and inclusiveness. So what we did was first we used the SciFact dataset that was present in Hugging Face, but it has very less amount of data that were present. So we generated synthetic data to tackle that issue. We have many technical issues as well because there were tensor mismatches, like while using PyTorch, there were tensor mismatches, because of which we use a contiguous trainer to avoid the safe mismatch during it. The key error was here because the labels which we generated were not matching, so that's also we tackled. Regarding the torch vision, like we used transformer and torch vision as well. Like torch vision was not that much used, but because both of them, Torch Vision and Transformer, have some modules that were overlapping, so that created an issue for us. So we resolved it by specifying the versions that we were going to use. Now we have the RAG adjustment. We use E5. We tested about like the number of top searches that we needed for the retrieval part. So we tested it with many of the numbers, and we got that 3 is the best to go with. Now about the conclusion. So we concluded that our model is 89.3% accurate, and it can be more if we just increase the amount of data set that we we had trained, and the numbers of epochs if we can increase, then it will be much better for us. And yeah, we also didn't have much documents that to create a knowledge base out of it so that we can improve the work of the retrieval part. Okay, what we can do in the future is like expand the data part, retrieval enhancement. We can deploy an app because the model we have now is not just accessible to normal people because they can't run it through all. So we can deploy a web app so that it can be accessed to them. We can use multi-model integration. Like for now, our model just uses text generation and then it works on it and like give us a myth and all. We can add upon one or more facilities that we can use images, which we can use for CNN so that image can be classified as well for the same thing. So we can integrate that as well in our future works.
The references we have used is the SciFact dataset, which help in generating the scientific claims are true or not. Then we have also used retrieval augment generation as we are using RAG for the knowledge base. As he has already talked about the future scope, I would like to add a little point to it. So as we do not have a more amount of a data, but what we can do is in future, as we are retrieving any data, we can save that particular data also in our knowledge base for further in future. If we would like to search it, it will not go all through the steps and search it, but it will directly retrieve from our knowledge base rather than going to the web and searching it again. Then we have used the domain specific language model pre-training. Hugging Face was obviously used for the scientific database, and Grok API documentation was used as we need to change the labels and how we are retrieving the data formats.
Okay, for the idea that you provided, it was good. We will slowly incorporate it further. Now, going on to the acknowledgement part, we would like to thank IITDM Jabalpur for the organizing this deep learning summer school. It was a very invaluable opportunity, a learning opportunity. We learned a lot, the concepts about various deep learning models and the concepts. And we would like to thank Rakesh sir for conducting this and it for the continuous support throughout the program that he provided to us. The tools and platform that we use is Hugging Face Transformer for model training and inference, Grok API for explanation and generation, Fires for similarity search, Tably for a web search because might be sometime there will be a cases that we don't have much data present in our knowledge base, so web search could help aid for it. And we use Google Cloud for experimentation and environment. So we thank you, everyone who is included in the Deep Learning Summer School. It was a very good opportunity for us to learn and showcase this project as well. Thank you, everyone.
Thank you, Khushi, and thank you, Shoshik. You both delivered a really well-explained presentation here. So do we have any questions from the panelists? Okay, so moving forward, first of all, once again, thank you both of you. And
Thank you, ma'am.
yeah, now moving on, we have Manya Agrawal.
Hello.
Yes. You're audible, Manya. Can you please share your screen?
Yes, ma'am.
Yeah.
Is my screen visible, ma'am?
Yes, it is. You can continue.
All right. So, hello everyone. I am Manya, and this is our project Tomato Leaf Disease Detection using deep learning. So, the problem statement is that tomato crops are widely cultivated but often suffer from diseases like early blight, late blight, leaf mold, etc. Farmers usually detect these manually, which is slow and inaccurate. So, we built a deep learning model to automatically identify these diseases from the images of the leaves. So the motivation is that this project fits into those computer vision as well as smart agriculture track. And for this, the early and accurate disease detection helps farmer take action quickly. So which actually reduces the crop loss and also limits the pesticides use. It will also open up the scope for real-time solution via mobile apps and drone vision systems. Research also shows that CNNs perform very well in image classification tasks. And for this model, we've used pre-trained model like ResNet 18 because it is helpful when we don't have a huge data set. For this particular model, we have used a plant village data set, which is widely used for agricultural image tasks. As far as the dataset description is concerned, uh, we've used a subset of the plant village dataset from Kaggle, and it contains labeled images for tomato leaf diseases. We have selected 3 classes for now, that is early blight, leaf mold, and healthy. And we've used about 300 images per class and split them into train, validation, and test sets. As far as the model architecture is concerned, we've used a pre-trained ResNet 18 model that I discussed before. And we've used the concept of transfer learning here, where we removed the final layer and added our own layer to output the 3 classes, that is early blight, leaf mold, and healthy. Also, we have just trained the final layer because we need to reduce the training time and avoid overfitting as well. Uh, we've trained the model for 3 epochs now just to save time, and we've used the Google Colab's GPU. Also, we've used ADAM optimizer and cross entropy loss function because it is a standard for these type of classification tasks. And we've kept the learning rate low because it is a good start. Also, we've used basic data augmentation techniques like random cropping and horizontal flipping. As far as the results are concerned, we've got an accuracy of 73.99%. This is a bit low because the model confuses itself between the early blight images and the leaf mold images, as I can see in the confusion matrix. Because the model classifies the healthy images and the leaf mold images quite good, but the early blight images are a bit confused between the leaf mold images as well. And we can see this in the classification report as well, where the precision for early blight images is pretty high and the recall is a bit low, which indicates that the model predicts the early blight images, but it does not image the correct early blight images. Also, leaf mold images, the recall is pretty high and precision is a bit low, which indicates that the model uh, basically predicts the images even when it's wrong. And healthy is a bit balanced, it's fine. So, considering the sample predictions, as you can see, there is a bit error in the early blight images because it confuses between the leaf mold and healthy images sometimes. But this is the result. And as far as the challenges are concerned, first of all, we had considered the huge data set that we had used, but so it was taking a lot of time for training. So we had to reduce it. And we have to use subset sampling for that. And there was some, as you can see, that there was an error between in the early blight, that the early blight images were not being predicted early. So it was a lot more when we were using the whole data set because there is a disease called late blight. So it was confusing a lot between early blight and late blight, and the accuracy was going really low. So we had to cut short the data from. We had to cut short that class as well, and there are some visual similarities between the classes. Also, uh, the conclusion that we've reached is that we've built a lightweight disease detection system, and it can be future. It can be integrated into mobile apps or drone systems in future, and we can also use it for more plant diseases. Thank you. Any questions?
Thank you, Manya.
Thank you.
So thank you for that insightful presentation and well explained presentation. We would be moving with our next participant here. Do we have Sohang Devnath with us?
Yes.
Yes. Please share your screen and you can continue with your presentation.
Yes, ma'am. Am I visible and audible?
Yes, you.
So let me hide this. So greetings everybody present here. I'm Soham Devnath and I am currently pursuing BTech from Kalinga Institute of Industrial Technology. So basically I have tried to make a model on pneumonia detection using modified ResNet. So this work falls under the domain of deep learning in healthcare, focusing the automation of diagnosis of pneumonia using chest X-ray images. So first we move to the problem statement. So for the scope of study, this project focuses on developing a deep learning based model to detect the pneumonia from chest X-ray images. The study uses transfer learning with a modified ResNet architecture to improve diagnostic accuracy and generalization of limited medical data. For the relevance, pneumonia causes significant mortality rate globally. For example, if you see the recent cases, the COVID-19 after the after effects of COVID-19 were pneumonia only. And in fact, right now there are cases, there are still growing cases of COVID-19, and as usual, the after effects are pneumonia, are high issues of pneumonia. So I tried to make a model in such a way such that it can access the X-ray images and detect early if the person is suffering from pneumonia or not, and help and support the overburdened healthcare system. So the research question is whether or not this ResNet model or the modified ResNet model I've made will work or not. So motivation and relevance as I've already discussed the relevance that I'm using this to predict pneumonia, because pneumonia is as it is saying a leading cause of death worldwide. But the thing I'm majorly focusing is that I am not making a particular CNN based model of my own. I am trying to use the ResNet model and trying to modify it such that the accuracy and the accuracy increases and loss decreases. So here's a literature review. So before we understand my model, so we need to first understand what is the ResNet. So basically from where I have get the data, that's the Kaggle. There many people has already contributed. Even in this session also I have seen a participant who has done the same work. But the thing is, I haven't used vanilla CNNs or mobile net. I have tried to use ResNet and try to modify it. So what explaining the ResNet, this is a simple diagram. If we explain in mathematical way, so basically these all layers are the functions from where the input passes, and input is nothing but an x, and we can say this as f of x. So the output of this diagram is nothing but f of x, x equals f of x plus x. That is, I am not building a model from scratch, but instead I am acknowledging the model that these are the few changes that can be added to the existing model. So here's the dataset description. So yeah, it is a normal X-ray of it is the X-ray of a normal person, and is a X-ray of the person who is suffering from pneumonia. This bloodiness you can get it from that person is suffering. So the dataset I've used is chest X-ray images pneumonia from Kaggle, contributed by Paul Timothy Monet, and it contains chest radiographs, and there are basically two classes here: normal and pneumonia. So their the total images is 5,863. Training are 5,216 images. Testing 624, and validation 16 images. So classes, there are two classes basically: normal and pneumonia. As you can see, the class distribution, the pneumonia the images which contains pneumonia are higher than the normal people. And also the images are resized to 224 into 224 pixels for the ResNet input, and the grayscale images are converted to 3-channel RGB. So let's understand the architecture. This is the basic ResNet 18 architecture for baseline architecture. So I have just included this in model 1 and just created a normal ResNet model. In linear, I have given input features at 512 and output features at the length of classes, that's the 2. So what I did to increase the accuracy is this modified ResNet model. So basically, I have created this ResNet model, and then I have added a sequential layer where I have implemented there is a linear layer which compresses the HD features from ResNet to a lower and more focused space. And obviously, we need to add non-linearity. Therefore, ReLU is there, and then there is a dropout. So why dropout? So when we are adding a linear layer extra, it was observed that the overfitting increased. So to reduce this overfitting, I have introduced this dropout, which randomly drops 30% of the activations during the training. Also, then for the final output, I use this linear layer from 256 input features to 2 output features, that is for classification of normal and pneumonia. So these are the training strategies, hyperparameters. This is optimizer, that is I've used ADAM, loss function, I will cross entropy loss, and epochs, there are 10 epochs I've used in this. Batch size is 32, learning rate is 0.001. For data augmentation, see, if you look at this is the data augmentation part. So for training, I have used flipping, rotation, rotation for generalization, resized, crop, normalization. So data augmentation part is quite big here. The reason is I want to train it in a harsh way so that it can detect. So while testing, it can easily understand the person suffering from pneumonia and person who is normal. Also, you can see here there is a I have used the reduce LR on plateau, which basically it helps to modify LR according to need. For example, when we have reached to a certain level when accuracy cannot be increased, the LR will gradually be reduced by the factor of 0.5, as I mentioned here, by a factor of 0.5, and mode is max, as I mentioned. Therefore, validation accuracy should be maximum. So let's come to the results. So here is the modified resident confusion matrix and original resident confusion matrix. For the original one, you can see that this higher recall for pneumonia is there, but there are misclassifications. For example, you see that there are 55 here and 6 here. Therefore, the overall data is not balanced. But for example, if you see this modified ResNet, the fewer false positive for normal, here fewer false positives are there, but there is a better overall balance. But okay, so it can be easily understood that this is a better model. So if you now we will see the accuracy graphs. So here train versus test accuracy for modified ResNet is somewhat like this. So here I guess it is 90, more than 90. Okay, so this is for 10 epochs, and for after 10 epochs it is like 90 plus, so 91, 91 point something maybe. For test accuracy, train accuracy is also good for about 96, I guess. And this is test accuracy and test accuracy for the ResNet, normal ResNet model. Actually, this is for the last 5 epochs. Don't get confused by looking at this 5 epochs. Actually, these are for the last 5 epochs out of 10 epochs. Why I did this, I will be mentioning in the challenges I faced. So you can see this, it is less than 90, that is 89 point something. So our model is slightly better than the original ResNet model. We can get it from this. So it is a modified ResNet loss curve here, and you can see the epoch 1 train versus test. Here it is all given. So this also contains the last 5 epochs out of 10 epochs. See, this is the train accuracy is 96.66% and test accuracy is 91.41%, which is I guess higher than other models. I won't say all model, but it is understandable. So these are challenges I face. First of all, the class imbalance for majority of the samples level as pneumonia causing bias learning. So for that I use data augmentation. And overfitting, as I mentioned, I used this dropout. And then this is the major challenge I faced: the collab hardware bottlenecks. First of all, when you are using collabs, you are only permitted to use for a certain amount of time. Therefore, you cannot work for long duration, and that was a major drawback. And also, when I was using for 10 epochs, the resource graphs looked like this. So see here, system RAM, it was totally overused, and after 6 epochs, it suddenly terminated, and the interconnection was disconnected, and I need to start it from beginning. So that was the major issue here. So I need to go for 5 epochs at a time. So here is the conclusion. Modified ResNet architecture, we have seen that modified ResNet architecture is good and with respect to normal ResNet architecture, though it is only difference of 2%, but still it's greater. Also, the normalization and dropout and batch normalization, these have also affected for data recognition. The project confirmation confirms the strength of the deep transfer learning for real world and healthcare applications. For future work, maybe we can use Streamlit as the other participant has done to predict, so that every doctor can use it. Also, this entire model was based not for or on the basis of making predictions only for making predictions for pneumonia or not normal people, but it was also made so that the doctors or those who are looking over this, so that they can easily understand, because their prime focus should be on curing, so they should be more focused on that part only. So if the model is very simple to understand and does all the work in a and the accuracy is also good, then I guess doctors will be, or those who are treating will get benefit from this. And these are the reference I used. for my presentation as well as for preparing the PyTorch model. And so also, though I didn't have the time to make that acknowledgement slide, but still I would like to acknowledge IIT Jabalpur for conducting this AI summer school, as well as I would also like to thank my professor, my institute professor, Mainak Bandyopadhyay sir, for letting us know about this program. So it was all a worth. Thank you.
Hello, Soham. Am I audible?
Yes, sir.
So why you have selected this model ResNet, not any other? Is there any specific reason?
Sir, actually, I actually searched for if there is another better model for this, but actually I got also that DenseNet model was better, but I wanted to keep it very simple. I don't want it, actually the DenseNet, with respect to DenseNet, this is a very lightweighted, and also you can actually, sir, in collab you have got very less time, and I showed you, sir, this thing system. And if I use DenseNet, I wouldn't have even allowed to run this 5 epochs also, I think they would have already only allowed me for 3 epochs. So I wanted to just train the model in a lightweight so that it would be easy to understand what is happening behind the scenes. That's why, sir.
Okay, thank you.
Sir, any feedbacks you would like to provide me?
Okay, thanks a lot, Sohang. It was a really
Thanks, ma'am.
well explained presentation and really insightful one. So,
Thank you, ma'am.
yeah. Now moving on with our next participant, we have Shri Prada.
Yes, ma'am.
Yes, okay. Shri Prada, please share your screen
Yes,
and you
ma'am.
can continue with your presentation. And I'll request, please try to keep it in the time
Yeah,
frame.
ma'am, sure.
Okay, thank you.
Is my screen visible, ma'am?
It is visible. It is.
Okay. Good afternoon, ma'am, and a very good afternoon to all the respected panel members and and all the participants. So my project is diabetic retinopathy detection using deep learning. I trained a deep learning model, specifically a fine-tuned ResNet 50 architecture, to classify retinal fundus images based on the severity of diabetic retinopathy. So basically, it's a eye disease. So my goal was to create an efficient and accurate model that can assist ophthalmologists, that is eye doctors, in early diagnosis, preventing vision loss. The things I've considered to pick this project are: number one, diabetic retinopathy is one of the leading causes of blindness, especially among working age adults. Many people approach doctors only when the symptoms become very severe. By then, the disease has already progressed. So, early detection can save vision of many. Number two, manual diagnosis of this fundus images is very time consuming. As a part of this project, while I was researching, I've got to know that there in countries like USA, they've already implemented models which detect this diabetic retinopathy, and they're used in hospitals. But the Google is also doing some active research in this part, and due to the image quality difference, India has not yet applied this. And there are big organizations which are taking images from local hospitals and doing them manually. So this model might be very helpful. The aim is to build a model that can automatically classify images into different severity levels. This speeds up diagnosis and supports doctor. So the dataset I've used is the Aptos 2019 dataset. It consists a total number of images 3,662, and I've taken this from Kaggle, and it have these 5 classes as shown. So the challenges in this dataset, I've faced many challenges, and one of them is class imbalance. As you can see here, a particular class has a high number of images, and whereas the other classes have very less number of images. So this was a major problem I faced, and also the blurred images and limited set size also was a problem. So I initially started with the DenseNet model. I've used this pre-trained model and I've tried to fine tune it on my model. And I've trained it for like 10 epoch, and I've seen that the training loss kept on decreasing gradually. And the validation accuracy was also increasing until the 7th epoch. And after that, it decreased a bit. And yeah, this is the graph where this is the blue shows the loss and the orange one shows the accuracy. Then I've also tried using it. I have also tried to train a pre-trained ResNet model, and I've trained it for like 5 epochs, and I've seen that the loss was decreasing and the accuracy was increasing. And at the 4th epoch, I saw that it was showing accuracy of 82%, which was better than this DenseNet model. So I've considered to continue with this ResNet model, and to make this, I continued to improve this model even more to get better accuracy. So this is the graph showing the loss and accuracy. So as we've seen that there was class imbalance, I've tried to add class balancing, and I've tried to increase the number of images in each class so that each class will have equal number of images. And then I've also added a few more layers like dropout layers and activation functions like ReLU, because I assume that the decrease in loss may be because the model is not understanding the or extracting the actual patterns. So maybe I thought it was overfitting, and to achieve generalization, I've done this. After updating the model, I trained it for like only 3 epochs because the collab was not supporting and it was very time consuming. And I've got the decent results for accuracy, and the training loss was also decreasing. So yeah, as I've gone through this research paper, I've observed that many of the research papers are effectively using this transfer learning, and especially in this paper, I've observed that they use pre-trained models like Inception ResNet V2 and Inception V3. Their model's accuracy was a lot better than mine, but yeah, I've used this approach of fine-tuning in the models I've implemented. And this is the image of I personally collected fundus images from my mom's hospital with proper consent, and I took these high quality images, and I would like to test my model based on these images. And conclusion, yeah. So this is what I've done. ResNet, I've taken a ResNet model and I added balancing and I've added few more layers, and that actually gave me best results. And I would like to train them more on more epochs. And I would also like to continue by adding Western data with Indian data and try to train my model on this at future. Yeah, I would like to take a moment to thank the summer school for providing me this opportunity, because in just a month, starting from complete basics to building a project, it is very overwhelming. Thank you all.
Which method you have used for class balancing in the case of your data is image, right?
Sir?
Can you name the method you have used for balancing the class?
Yes, sir. I have actually taken this resample function from Python. It's like duplicating the images to increase the number of images. But I've also tried with the
Just
weight
a
random
random
sampler.
sampling, you can say, right?
Yeah, sir. And
Yeah.
weight random sampler also I've done to give weight to less ones.
Okay, I think. Okay, thank you.
Thank you, sir.
Hello. Yeah. So thank you, Shri Prada. We will be moving with our next participant, that is Shri Prada. Sorry, Udita Monani. Do we have with us Udita Monani?
Yes, ma'am.
Yeah, sure. Please share your screen and start with your presentation.
Yes, ma'am. Is it visible?
It is visible.
Thank you for confirming. So, good afternoon, everyone present here, the organizers and the faculty members and the participants. I'm Udita Munani from Kalinga Institute of Industrial Technology, and I will be presenting a presentation on a project that I've done that is based on SAR and optical image pairs. I've tried to map the SAR images with the optical images. In fact, I've tried to convert them to optical images. So SAR stands for synthetic aperture radar. These images are generally useful when we try to capture satellite images, like through a satellite. When we try to capture an image of the Earth, there is generally cloud cover that comes in the middle. So optical images don't play a very good role here. So the SAR basically emits radio waves or microwaves depending on the range of the satellite and the devices used. And the amount of backscatter that happens through the Earth, it creates an image based on that. So this is a very novel approach, and it has been used since quite some time now, but still there is not much research done on this. And yes, the main gaps that were there was that SAR and interpretable optical imagery was not always considered to be a very good pair. But I think this can be the future because enhancing 3D features is very important. And also, uh, land cover classification can be done. So the challenges that were there was obviously the cloud cover first, poor lighting or adverse weather conditions for optical imagery. And SAR imagery is always available as already written, but not very easy to interpret for me and for people who don't know about SAR imagery. And the research gaps that I found from other papers were SAR images generally have something called speckle noise and radiometric noise, which is mostly ignored in all the research that was conducted earlier. They did not remove this noise, neither did they consider to minimize it. So most methods consist of single domain classifications, and they don't have efficient models for it. I have not proposed a novel model here, but still I've tried to give a research gap some limitations. So the primary objectives were I developed a conditional JAN for effective SAR to optical image translation, and I used a unit generator because unit is the best model that we know for segmentation as of now. And unit with attention. When it is combined with attention and removed the skip connection part, then it gives better results. These are the applications of the images. Slides are not very professional. I did not get time to do it. I was mainly concentrating on the project. So yes, visible light range is this many micrometers, and the key concepts are already visible here. So spatial resolution is basically the scale on which the images have been taken. The images, optical images generally are not very scalable on anything. Like whatever we take through our phones or cameras are generally optical images. They have only three bands, R, G, and B, red, green, and blue. So the temporal resolution, spectral resolution, all of them are very much limited. So in SAR images, generally the number of bands are more. They are black and white images only because it has been developed from backscatter, but the number of bands can be more based on the dielectric constant of the medium that is reflecting back the signals. So these are the concepts of SAR imagery. They have active sensing microwaves at C band. So they can be constructed at all weather, penetrate cloud smoke, and sensitive to surface roughness. So basically, water has a very low dielectric constant. So it reflects back very less. So whenever a microwave goes and hits a water body, it does not reflect back much. It absorbs the light. So in a SAR image, whatever dark patches you can see, comparatively dark patches rather, so you can somehow classify them as water. Obviously, we need the ground truth values, but initially you can classify them as water just through your naked eye without using any models. So this is what we had got initially. So the SAR input was there and the optical input and what I generated as the optical. So we did it for 10 epochs and the 10th epoch did not give very good result. But after every 3 epochs, we tried to present the result. So we'll know this. So the data set that I took had 4 classification classes. Luckily, they were all balanced, not much of an imbalance I had to face. So agricultural land, barren land, grassland, and urban areas, all these things were already classified. So it was very easy for me to actually evaluate my model's performance because the ground truth values were already there. So I just had to map it with that. These were the challenges that I had faced. Interclass spectral similarity. Obviously, agricultural land and grassland both have somewhat green areas. So the dielectric constant will be similar. Not same, obviously, but similar. So the backscatter was also similar. And this was one challenge that I had to face. But based on the boundaries and the pixel values and the satellite components, I could figure out which is agricultural land and which was the grassland, though this can be done better in future work. So the satellite I considered here was Sentinel. There are more satellites like EO1, Cartosat, and all those things, but Sentinel gives good results when always taken for SAR. So Sentinel had these frequencies and polarizations. Okay, SAR images have 4 types of polarizations, 5 in fact, 5 types of polarizations. VV, VH, HV, and HH. That is vertical, 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 horizontal, 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 vertical. These are basically the first V stands for, if we are talking about VV, the first V stands for if you are from the satellite, if we are sending a vertical wave and the way it comes back from the earth, like the backscatter, if the backscatter is in a horizontal direction or a direction that is more than 90 degrees away from the original one, then it is called as horizontal. So based on what you're sending and based on what you're receiving, the polarization is determined. So the spatial resolution and everything is given here. Generative adversarial networks is basically this, a generator and a discriminator. So it basically creates a fake data to fool the discriminator. This was there in the exam as well. So basically what I tried to do is the generator was the first initial microwave that we sent. And the second one, that is the discriminator, is the backscatter that we received. So based on the backscatter, it created some data as the optical data. So I tried to map it with that. And the function is also given here. The function that I use basically, which always also exists. Yes, gradient vanishing was a very difficult thing. But again, it was not very difficult because I considered removing the speckle noise and the radiometric noise. So initially the weights were quite good. So conditional GANs were used. The advantages were already given here. Suitable for paired image-to-image translation tasks. We all know this, already taught in the classes. And it preserved the input-output correspondence. Basically, it mapped the input with the output. So it was easy for me to just find out the performance of my model at the end. And coming to this, this can be used. So this is not what I have done, but this can be used in future. The data flow was input was the 128 cross 128 single channel SAR images. Single channel meaning there was only one band, luckily, so I did not have to reduce the dimensions, else PCA could have been applied. So the generator I used was unit with skip connections. With attention, it will obviously give better results, but let's keep it to the basics and use skip connections initially. So skip connections, and then the output was synthetic optical images, which was of the same size and RGB because they are optical. So discriminator was the binary classification, that is the synthetic versus the already optical present, and the optical images that were present were corresponding to the same area as the SAR image area. So it was not very difficult. Okay, this is the data set. The challenges of the data set, which has already been discussed once. So the data set was balanced, 50 training and 20 validation per class. So yes, now network design. The network that we followed here was, yes, unit generator architecture. This is the encoder bottleneck and the decoder structure. It was just 4 levels with Karn 2D, batch normalization, and leaky ReLU. We considered leaky ReLU because vanishing gradient problem. Now dying ReLU was also a problem here, but the number of feature channels, that is 512, as you can see here. The number of feature channels reduced the dying ReLU problem significantly. It did exist, but still it was reduced to quite a good level. The decoder and everything you can see here. The skip connections were there between the encoder decoder, and the TANH activation for normalized RGB values was used. Why? Because TANH has its range from -1 to 1. So this is the most simple thing that we can do here. This was the architecture of the discriminator, just a simple explanation given here for the network design and the structure of the layer. So for binary classification, 128 to 1.2D layer was used, and no final activation was used because we used the logit function. We needed it from 0 to 1 instead of -1 to 1. So we used no activation as such. Now the loss functions and the training strategy that we used was this. So Jan loss that always exists in networks that we use, and L1 loss, that is mean absolute error for pixel-wise reconstruction, because the SAR images were taken to a matrix form. Based on the number of pixels per based on the number of bits per pixel and based on its polarization, it was constructed as a matrix, and then pixel-wise reconstruction had to be carried out to convert it to optical images separately. So this was the training strategy that was used. Discriminator trained on real and fake pairs separately because we also had to map it with the original optical images. One more challenge that I faced here was there was no metadata available for this data set specifically. So it was quite difficult to find out whether what pixel had how many bits. But however, I found out here each pixel had around 2 bits. So that is good for Sentinel. So that is one thing I faced here. And hyperparameters just mentioned here, also there in the code. So memory management, I had to do it because Colab is very inefficient in this. Sorry, but it is inefficient. And the dataset size was 32,000 images. So it was not very good. Batch size had to be implemented for resource constraints. I used T4 GPU, though not very good results were there. Session had crashed many times. So the pipeline is here, resize all images, normalize them for -1 to 1 for stable training, augmentation, like horizontal flip. That was very random because it is not possible on Colab to find out what is the polarization of each and every image. Also, there was no metadata that I could map it with. And yes, brightness or contrast variation was there for optical images, but optical images were luckily used only once to find out the ground truth. That's it. Also, one more thing. There were TIFF and TIFF files. There was no GeoTIFF file available. So in GeoTIFF files, we have the coordinates with us. If the coordinate would have been there, it would have been more easier to find out the image from directly Google Earth, and we could have mapped it with the SAR data. But that was not available in the data set itself. So these are the training losses and the balance, generator and discriminator. The dataset structure was this: memory management and training stability. These have already been discussed in previous slides. And yeah, the results are here. So loss evolution was this from epoch 1 to epoch 10. But the last epoch again did not give very good results, as I said. So 9 epochs we considered and 19% improvement approximately. So that is a good thing for this research, as previous research did not consider this much. The discriminator loss was this, good balance almost. L1 loss component was decreased from this. It's already there on the screen. So converging generator loss, yes. So the data initially appeared to be diverging. When we were considering the dynamics of the data, it initially was diverging, but for any model to be very efficient, it has to be convergent. So converging generator loss was there. So I'm sure it was learning very well. So this was the main results that we got. So for each and every class,
Kindly
these were the
conclude the
results.
presentation as soon as possible. One more
Sorry, sir?
presentation. Conclude the presentation.
Sure, sir. These were the visualizations. So for the third epoch, as I said, every 3 epochs it was there. So for the third epoch, this is what we had got. So the generated optical is not very mapping with the real optical, but afterwards it is mapping in the 9th epoch. You can see Generated optical is mapping with the real optical better. So these were the quality metrics that were used. Just the graphs constructed from whatever tables was seen previously. And overall accuracy and everything was measured. Per class accuracy was also measured. Generator efficiency for other architectures can also be considered in future work, though I aim to do it. Just box plots considered. Limitations in future work, whatever I said here, can be considered with DenseNet and ResNet in future. Lightweight ResNet and robust data handling. So these were the main contributions that were there. And that's it mainly. I would really like to thank the summer school for providing me this opportunity. And thank you. Any questions?
Thank you, Udita. It was a really well explained presentation, and we got a lot of insights. Some new topic we understood today. So thank you once again. Now, we'd like to move with our last participant for the session, that is Vijeta.
Yes, ma'am.
Yes. Okay. So please share your screen and try to keep it in the most brief way possible.
Yeah. Is my screen visible, ma'am?
It is visible.
Okay. So, just a second. So, my topic, good afternoon, everyone. My name is Vijeta. I am BTech's third year student now from KIT University. So, today I'm here to present my project, which is Plant Health Detector, Automated Leaf Disease Identification using CNN. In a world where AI is transforming industries, we are now empowering one of the oldest professions, which is farming, with cutting edge technology. So, just a second, my mic.
You're audible, Vijeta. I think you can continue.
Okay, ma'am.
Okay, try sharing it again or closing the
Oh,
tab and
yeah, sure.
reopening it. Okay,
Sure, ma'am. Sorry for the inconvenience.
no problem.
Okay. So next we have the introduction part, which is I would like to tell you about the agriculture. Agriculture is still the livelihood for over 60% of people in developing countries. Plant diseases not controlled early can wipe our entire harvest. Unfortunately, many farmers can't afford expert help. Here, AI act as a silent expert, always available, always learning, always improving. So this is my model to help the farmers to detect the problem. So next one, we have our problem statement. So did you know that every year 20 to 40% of global crop yields are lost due to plant diseases? Farmers often rely on visual
Pardon me,
inspection.
Vijeta. Please move with your architecture of your model and then
Okay, ma'am. Sure, ma'am. So yeah, this is my architecture of the model, which is the heart of the model basically. So the model starts by resizing images to 128 cross 128. It then passes through three convolutional blocks that extract important features like textures, colors, disease patterns on the leaves. So my convolutional block consists of three parts, which is convolutional layer, ReLU activation, and max pooling. So each convolution layer captures increasingly complex patterns. First layer detects simple edges and textures. Second layer captures shapes and leaf structures. The third layer detects high-level disease patterns. Increasingly filters switches to 32 to 64 to 128. Allows the network to extract more detailed features as we go deeper. So after the feature extraction, the data is flattened and passed into fully connected layers. I also use dropout layers to prevent overfitting, and finally, a softmax layers classifies the disease.
The model is trained with Adam optimizer and force entropy laws, making the learning smooth and stable. So these are my hyperparameters and learning strategy, which includes the model was trained with the learning rate of 0.001, batch size of 32, 10 epochs, 40% dropout to handle overfitting. I think this would be the safer side. 10% validation split to ensure generalization. I used the simple hyperparameters, but they worked wonderfully for this problem. Now, about the results and the classification report, I will tell you that yeah, because my data set was large, so I can't just paste it on. This is the classification report I got. It includes the precision, recall, F1 score, and support. Everything is there in the report, and I also print the confusion matrix to just show the results and the disease it detects finally, and also the pictures that it is how it detects. It is the tomato healthy, it is potato early blight, and bell pepper healthy. So these were the outcomes from my model. And next we move on to the challenges I faced. So firstly, obviously, of course, building a model was not without challenges. So data challenges, which is the data set was imbalanced. Some diseases have very few examples, variations in lighting, image angles, and leaf quality also. About the model challenges, overfitting was a real risk with limited data. Data models needed high computational power also. But as we face challenges, we also led to the solutions also. So I used the data augmentation, made the data set richer and more diverse. Class weighting helped balance the learning. Transfer learning reduced training time and improved performance. And about the conclusion and the future work. In conclusion, my CNN model successfully detects plant diseases from leaf images, achieving high accuracy without manual future engineering. So in future about scope you are asking, more data augmentation can further improve generalization. I would also like to make the apps that farmers can directly upload the picture of the diseased plant or the leaf, and then it will detect or through the app only, so they will get to know as early as possible. About the references, I use the plant village dataset, which is from Google, and it is a vast dataset, includes all the leaves and all. So it gives the variations also about the frameworks and libraries, and I also take key research papers, which helped me a lot. Then, obviously, I would like to thank the IIITDM Jabalpur for this opportunity to meet me, and I learned a lot through this 1 month program. And thank you so much. Thank you.
Thanks a lot, Vijayata. This means a lot to us. Thank you for the acknowledgement and also for such an amazing presentation.
Thank you, ma'am.
Yes. So now, since we are towards the conclusion of today's presentation, we have done with our last presentee. I'd like to thank you all the presenters for their inspiring and thoughtful work. I mean, your projects clearly reflected the knowledge, creativity, and dedication that you have cultivated over the past 4 weeks. It's truly encouraging to see how each one of you has applied deep learning techniques to tackle these amazing and varied real-world life problems in such an innovative ways. And we hope that it's just the beginning of a journey into your world towards AI. Here, before we close, I would like to invite our esteemed panelists, Professor Jimson Mathew, Dr. Ranjeet Kumar Ranjan, and Dr. Ravi Ranjan Karn. If any one of you would like to share a few closing remarks or words of encouragement with our students, it would be really good. We are honored to hear from you.
I have seen all. Am I audible, Nisita?
Yes, sir, you are.
I have seen all the presentation and most some of the presenter I think in BTech first year I guess, and based on the presentation and the content, based on the experiments, I think their future is very bright. They are doing very well, and I would congratulate all the students who had presented, who had participated in the building Capstone project. And also we'll congratulate to all the students who have attended the summer school and we looking forward to collaborate further in order to means as we know we can collaborate for further research. So you can contact us, any of us. So thank you so much, and once again all the very best. Thank you.
Thank you, sir. If any other panelists would like to encourage the children, it would be really great. Okay. So we'll be moving forward then. Thank you, sir, for your kind and insightful words. Your encouragement means a lot to all the students here. So with that, we conclude the student project presentation session. Thank you all once again to all the participants, panelists, and audience for being the part of this amazing morning session. Wishing you all continued success and growth in the field of AI. Thank you once again. So all the panelists and all the participants, you can leave. And with this note, I'd wish you all a great day. Thank you all.
Thanks, everyone.
Thank you. Thank you for a great session.
Well, it's all because of all these amazing participants. So thanks to all the participants again.